we're just going to give it a couple of minutes for people to start filtering in. Seems to be a gradual process for some reason. All right, give it just maybe another minute. So just while we're waiting, we are recording all the talks, and we should get those posted on our website in the next couple of days. Just pending the speakers themselves being approving of that. So okay, let's get started. So it's my pleasure. Welcome back, everyone. It's my pleasure to introduce our first speaker for our second session. So Sam Burden is an assistant professor at the University of Washington. So Sam may not be familiar to many of you in the audience today. Sam is a real control theorist. He uses control theory in a much more formal sense than we typically see at these kind of meetings of human mode control. So Sam works on problems like locomotion in legged systems, human in the loop, and feed forward versus feedback control. Just understanding these in a bit more formal and rigorous sense than we often approach it. And I think the insights and approaches that he uses, I think, can be very useful for us, and has in fact already influenced some of the work that we do in my lab. So with that, I'll hand over to Sam and look forward to hearing your talk.
Super, thanks so much, Adrian. There we go. You folks see my slides? Fantastic. Yeah, it's a real pleasure to be participating in this meeting and getting a chance to talk to you folks today. I'm really excited to share some of this work, and like Adrian said, I'm a control theorist by training, but I'm really interested in particular sensor motor control theory and developing kind of new theoretical computational techniques, but also doing real experiments and applying them to real systems. So in a lot of ways, a lot of my work is strongly informed by the work of this community, the kind of scientific advancements and understanding, and potentially, to a degree, some of the techniques that we develop on the engineering side may be of use in your work as well. So I'm hoping that you might find something today potentially useful. And by the way, the slides are available. So if you want to follow along, you're welcome to grab that link and download them, so you can flip back and forth and things like that if I'm going kind of too fast. I have a habit of talking a little quick. So the leaping off point for this talk is the observation that human interaction with the physical world is increasingly mediated by machines, and these are not the kind of passive machines of yesterday. These are adaptive, potentially intelligent agents that are learning and adapting and changing their control strategies over time. And the kinds of contexts that I'm particularly interested in are situations where humans are kind of inevitably in the loop. So it's not, semi-autonomous driving where, okay, we should just let the cars drive themselves eventually. It's things like surgery or things like neuroprosthetics or things like, human augmentation or exoskeletons or things, even for able-bodied people, that I find kind of most exciting. And, we saw this wonderful presentation from Jennifer Collinger yesterday, kind of highlighting that work here in the middle. And my basic question is, once we plop humans and machines together and we start considering not just the learning of the human and how they control their own body, but how they learn to interact with some external, complicated, dynamical machine. I'm interested in that. And then how the machine should correspondingly learn and adapt to the person. So that's really the driving question for a lot of work in my lab and the framing for today's talk. So the talk will come in two parts. First, I'm going to focus on our work studying things like feed-forward and feedback control, trying to characterize, get a better quantitative predictive modeling understanding of how people control or how people learn to control machines. And then in the second half of the talk, I'll give some of our more recent work, stuff I'm super excited about, where we're kind of empowering the machines with this newfound understanding of how people will control and interact with machines, what internal models they will have. And so we give our machines their own internal models interacting with the person. So let's start with this first piece. And the paradigm that we use goes back a long time. Control theorists and ergonomics and human factors people have been using this paradigm for a long time. And it's basically, if you sit a pilot down in a seat and you give them a joystick control, and then you give them some display and you tell them what they need to track, then you basically set up this closed loop, this closed sensor-motor loop through this external machine dynamics. Just for notation throughout the talk, I'm going to think of the human's input to the system, through a joystick or other interface as U, and then the display that they get back, whatever sensory information is coming back, as output Y. In the old days, this was literally like a trace on an O-scope. Nowadays, we just use conventional displays or VR or other kinds of sensing modalities or things like that. So those are the sensor and motor signals that are really important for the system. And there are two other signals that are going to be very important. One is the reference, which is the trajectory that we are tasking the person with tracking. And the other is a disturbance that comes in kind of invisible, at least in our experiments, kind of invisible, not directly visible to the person, but corrupts or influences the input that they're supplying to the system in this kind of way that's not directly observed, but nevertheless they need to learn to adapt to and respond to. Broadly speaking, this reference we think of as corresponding to, Adrian brought up this feed-forward feedback, so I'll just kind of allude to it now. This reference is kind of driving the feed-forward response in the person, and the disturbance is driving the feedback, although they are actually intertwined. They're not kind of cleanly separable along those lines. So again, I'm a control theorist. So the way I see the world is through the magic of block diagrams. And so, taking that kind of schematic view in the previous slide and then turning it into one of these mathematical specifications I like. Our human is a block here. So basically, if you're not familiar with this kind of modeling paradigm, the blocks represent transformations and the arrows represent signals. So our reference signal, goes directly to the person. They can see the reference. The other thing they can see is the output or just the tracking error, and that's going to influence the output they produce, which is the signal U. And then in our experiments, we're going to just directly corrupt that input U with this additive disturbance before it goes and controls the machine. And so the first basic question I'm interested in is, what's in the box? So what's happening inside the person? What sensor or motor transforms are they implementing, and how do we kind of think about them? And of course, thanks to this community and kind of related fields, we have a reasonable guess about what's in the box. There's a lot of evidence, both theoretical and empirical, that the human motor control system may be learning. I'm going to call them system models. It's also common, and more common in your literature to call it a forward model, but just to disambiguate terminology, I'll refer to it as a system model. And then pair that with an inverse model. So if the system model tells, is the human's understanding of how their motor actions, lead to sensory consequences, the inverse model would be the flip of that. If they want to do a given task, if they want some output in sensory space, what motor command do they need to produce to elicit that? And just a small tweak on terminology, again, just to make things clearer for not the control theorists in the audience necessarily, but anyway, with the literature that I'm going to be kind of building on. I'm going to refer to this inverse model as the feed-forward model, because actually, as we'll see, humans don't exactly invert, at least in our paradigms, exactly invert the system models that we prescribe. They approximately do. And so it's nice to have a different term to kind of distinguish it. And in control theory, this is pretty commonly referred to as the feed-forward element of control. The other reason that I really like, there's a lot of different competing theories of motor control. The reason that we've really latched on to this, internal and inverse modeling paradigm is that it has really strong parallels in fields that I grew up in control theory, AI, more recently RL, things like that. So I think there's a lot of really rich, overlap and intersection in methods and questions and answers between these communities. So going back to this block diagram picture, what we're going to hypothesize is inside the box is some combination of feed forward and feedback. And in fact, we're going to kind of restrict the scope of systems we're investigating. We're going to restrict to the situation where our machine dynamics are linear, time invariant. So it's really, a really common paradigm in this field is the, manipulandum reaching in a curl field or something like that. Those are very non-linear dynamics, both of the arm and the manipulator itself, and then the imposed dynamics. We're going to restrict to linear time invariant machine dynamics. And the reason for that, as I'll show in the next slide, is that it gives us access to an extremely powerful suite of analytical tools that have really nice interpretations or applications in experiments. So it makes it really easy to interpret and manipulate experimental data when we restrict to LTI systems. And so under that restriction, then it's pretty natural to hypothesize that the two mechanisms at play inside the person are feed forward input based solely on the perceived reference, and then feedback on tracking error. And again, because things are linear, it's natural to hypothesize that those just directly superimpose. And so then here's an example of what's really powerful about this kind of control theory modeling paradigm is this block diagram is not just conceptual. I mean, at the beginning, I referred to it as a mathematical model, and indeed it is. It's actually equivalent to a set of equations, again, under the hypothesis that each of the block transformations inside the diagram are linear time invariant. It's equivalent to a bunch of algebraic equations that relate frequency content of the various signals, the R and D external inputs, the U and Y, the measurables, that have to hold if things are linear and if things are interacting in the prescribed way. And so to test this hypothesis that humans use this kind of combination of feed forward and feedback and look at what those different elements are, we can take this block diagram and just directly transcribe it into systems of equations, again, that have to be satisfied if this is the way that things are interacting. And then what's really powerful is, again, under the assumption of linearity, we can then solve these equations for the unknowns. We can manipulate the equations and solve for the unknowns, the things that we can't directly observe. I can't just look inside the person's head and find their feed forward model and their feedback model, or at least not yet. But what I can directly observe and measure is, okay, well, what is their response? What is the contribution of this reference input to the output from the human? And what is the contribution of the disturbance input to the output of the human? And so in these equations, once I've solved this, everything on the right-hand side of the equations is known or directly observed. And then everything on the left side of the equation is, not directly observed, but something I'm really, really curious about, what it looks like. And so we do these kinds of experiments. The first batch of experiments we did in my group in this space, we just did a one-dimensional trajectory tracking task. So this wiggly orange thing is that reference trajectory. The user's supplying one dimension of input to move this cursor through various kinds of dynamical models. And then what's not shown here is that invisible disturbance that's also kind of superimposing on the human's input and influencing the motion of the cursor, even though the person doesn't get any direct knowledge or access to what that signal is. And so the kinds of outcomes we get from these experiments, these first couple slides are just kind of reproducing known results, but I want to show them because it acclimates us to the different kinds of analyses and visualizations and stuff that I'll use throughout the talk. So the first observation is, humans basically learn to invert, say, a first order system. So first order means that they're commanding the velocity of the cursor. And roughly speaking, we get pretty consistent estimates of these feed forward and feedback controllers. The filled regions and the dots are basically two different estimates of the same quantities from two very different assays that experientially to the human, they're very different. They're doing very different tasks, even though we can estimate these quantities in both versions of the assay. So humans approximately invert, but they don't exactly, except at the lowest frequencies. Everywhere else, they're kind of hedging. They're kind of doing it, 80% of the way there or something like that. And so, what that suggests is, because of course, if they were exactly inverting, then they would do better at the task, at least in principle, holding all, everything else staying equal. And so what this suggests is that doing well at the task isn't the only priority for the person. They have some other, hidden priority or cost potentially that they're trading off. And that's actually kind of motivating and we'll return to that theme in the second half of the talk, but I just wanted to kind of see that hint here. If we do a different machine dynamics, second order, so the person's basically commanding acceleration, except it's slightly kind of damped. Similar sorts of trends apply. We get pretty consistent model inversion in phase. This is like more than a 90 degree, almost a 180 degree phase advance that the person has to do. They basically have to predict what the reference is going to be, a couple seconds into the future, or a second or two into the future. But then on the magnitude portion of this, they're again kind of attenuating. They're doing like 80%, rejecting like 80% of the disturbance, or tracking like 80% of the reference with feed forward. And the rest of their performance is kind of made up through feedback and things like that. So this kind of acclimates you to this basic experimental paradigm. The first kind of new application that we did in this space was to apply it to different motor modalities. So my student had this very cool idea of using, I would almost call it a neural interface. Okay, it's peripheral, but anyway, it's muscle, muscle electromyography on biceps, triceps. And we use that as the difference between biceps and triceps activation as that one dimension of input. And we compare the performance with this joystick slider. And we didn't really know what to expect. My naive expectation was the EMG interface was going to be way worse, because I understand that it's noisy and you have to kind of heavily filter the data to get anything sensible out of it and things like that. So the results we got were actually kind of surprising in that regard. So we can look at a couple different performance metrics. We can look at tracking error. So how well are they doing the task? We can also look at inversion error. So, with regard to the previous couple slides, how well is their feed forward controller approximating the inverse of the prescribed dynamics? And what we found is that, okay, we really didn't see statistically significant differences in performance in tracking error for the muscle and the manual interface. In inversion error for the first order system, we didn't see any big differences, but inversion error was significantly lower for the muscle interface for the second order system. So what this means, the interpretation, is that the subjects are doing a much better job instantiating the proximate inverse of the machine dynamics using the EMG interface. And there are a lot of peculiarities about our experimental setup that could explain this difference, but what it suggests to me as an engineer is that there is ample room to each different motor and or sensory modality is going to have different performance characteristics. One is not better than the other, they're just different. And there's an opportunity to think about kind of fusing them to get more effective interfaces. So that's a project that one of my current students is working on, this like sensor motor fusion, and how do we optimally kind of combine different motor modalities to get a higher performance human machine interface. Then the second experiment I want to talk about is we looked at handedness. So of course, probably everybody is familiar with this concept that a lot of people kind of identify as either right-handed or left-handed. You can actually quantify this in various ways, and so this seems to be a real phenomenon. So we were curious, what is the effect of performing this task with your dominant hand versus your non-dominant hand? Because in our field, these tasks had only ever been done with dominant hand, because they were mostly focused on getting experts to do the task or things like that, like pilots and stuff. And so we were interested in, okay, what happens if you're kind of less experienced with a hand? So we did an experiment with two different groups, two different populations. One of them, we had them use their dominant hand first to do the task and then switch to their non-dominant. And then we flipped it for the other group. And by the way, of course, dominant doesn't always mean right-handed, but as it turns out, in the two populations that we recruited, it just so happened that everybody was right-handed. And so I'm going to conflate the two in the second of the talk, although of course, in general, I shouldn't be saying R and L, I should be saying dominant, non-dominant, but just for concision and clarity, I'll just make that small kind of fudge. And so what we found, when people use their dominant hand at first, makes a lot of sense. If we look at tracking error, it gets better over time with experience. But then what we expected is that when they switched hands, this is going from dominant, like the hand that they're going to be, that you probably mouse with and write with and, do a lot of fine motor control tasks with, and they switch over to this fine motor task with their non-dominant hand. We expected, performance would definitely get much worse and then probably adapt over time, but we actually didn't see that. We saw performance maintain. And then in the other population, starting with non-dominant, we saw improvements in tracking error with the first hand. And then we didn't see any changes with the switch to the second hand. And so if we look at, just summary statistics, so histograms of this tracking error performance metric in first 5 and last 5 trials with each hand, and then you kind of switch, we see statistically significant improvements with your first hand, and then no changes when you switch hands, and no change with that second hand, even though you got the same amount of experience with that. And so the kind of takeaway here is that the hands are really performing the same in this task. So maybe handedness, at least in this context, isn't the right term, maybe armedness or something like that. And more provocatively, again, as an engineer, as somebody who wants to build systems that people can readily learn to use and get high performance, the performance seems to transfer between the hands. So we're really excited about this idea that we might be able to decrease training time and things like that. And if we look in more detail at the actual control strategies that the people employ, we see improvements in feedback in that first, with that first hand, and then kind of no changes after that, and no changes in feed forward. This also surprised me because the improvements that we're seeing didn't have to do with the people doing a better job internalizing and inverting the machine dynamics. They were actually doing great at that from the get-go. But what really improved was their feedback, and we think that perhaps sensor motor noise has a role in that. And there's some kind of fun results I encourage folks to check out if they're interested in that paper. Okay, so the takeaway from the first part of the talk is people adapt to machines. They internalize models of machines. That's readily apparent if we measure it. It also just logically makes sense, or kind of makes sense with experience in daily life. And so in the second part, and I realize that I don't have half of my talk remaining. I have just a couple minutes, but I'll still be able to get to some of the fun, interesting new results in this vein. I want to think about what it would mean to endow machines with the ability to model and predict what people are doing. And so the first observation is that I think the way we need to think about this co-adaptation problem is as a game, game theory in the sense of Nash and von Neumann and Morgenstern and Stackelberg. And I think there's a really interesting intersection, fresh kind of intersection between motor control, motor learning theory, like your community, and then these kind of more formal communities of game theory, control theory, and things like that. And I think this is a fun kind of catch-all term to capture that merger. And so I'm going to make a couple of assumptions to make the problem concrete, because of course, decision making is a very broad theory, field. There's a lot of different ways we can interpret how to make decisions. I'm going to take the simplistic view that the human and the machine in our interactions are seeking to minimize some cost. When it comes to walking, maybe this is metabolic cost on the part of the human, but when it comes to our little artificial in-lab experiments, we could potentially prescribe the cost, which is what we do in our experiments for the human, and kind of see how they respond. And then the other main modeling assumption or point I want to make is that I don't want to assume that either of these agents can globally optimize and get the best the absolute best thing in all circumstances. They're going to have to make decisions based on data, based on experience, and they're going to have limited computational resources. Broadly, this is captured by this notion of bounded rationality. And in practice, what it means is that our machines, I'm not going to have our machines running algorithms where they're doing global optimization. I'm going to have them doing something like stochastic gradient descent. And I might hypothesize that perhaps a person is doing something analogous, although we have some data to refute that hypothesis, or some other kind of simple adaptive scheme based on limited information, local data, local computation. So as an example of where this kind of game phenomenon can arise, I'll point to brain-machine interface, where a user, whether it's a human, as in Jennifer Collinger's wonderful experiments, or with the collaborators that I have here at UW, a non-human primate user, sees visual error between a desired target location and an actual cursor location on a screen. They produce some neural data, either measured directly from cortex, or maybe we're doing peripheral measurements or things like that. And then there's the machine's role is to decode that neural information to determine the cursor location on screen. And it's pretty common to design the machines using kind of an optimal estimation, state estimation kind of thing, like a Kalman filtering paradigm, in which case, really that, whether explicitly or implicitly, the machine is assumed to have a cost that's some combination of, norm of tracking error and then norm of effort produced by the machine, kind of captured by that second term. And so I think it's kind of natural to hypothesize that the brain has something similar, and other folks have made this kind of hypothesis as well. What's interesting is that automatically sets up this game, because now I have these two cost functions, which is over shared decision variables. The performance from the perspective of the human is influenced by the machine's choices, because that changes the tracking error, and vice versa for the machine. But the two don't have exactly aligned or identical priorities, because the human wants to minimize its effort and it could care less how much work the decoder has to do, and vice versa, the decoder is penalizing its effort so that it isn't kind of overfitting to the individual, or cranking up the gains way too high, or going unstable, or things like that. So there's this natural kind of tension in both within the two agents and between them, trading off performance on a task, so task error, versus the effort that the two have to commit. And so in this
about 5 minutes, Sam.
Super, thanks, Adrian. And so in this paper from this year with new collaborators of mine, Amy Orsborn, is a faculty in ECE, and our co-advised student, Manishka Maduri. We did kind of a theoretical analysis of this interaction, and we found that the stationary points, i.e. the Nash equilibrium for this game, have the really intuitive property, which makes a lot of sense in hindsight, that the brain learns to invert the decoder. So I'm excited about this line of work. We're now kind of taking this analysis and applying it to existing data sets that Amy has with non-human primates, see if we can get some interpretations of what the brain is actually doing in real experiments. But this paper has kind of a fun theoretical analysis of the interaction between these two terms. And then the final thing I want to get to is this new set of experiments, this new paradigm we're exploring, where we're really directly probing the sensor motor game that arises between when a human and machine interact. So what we do is we prescribe a cost function for a human participant. We prescribe a cost function for the machine participant. The human gets control over, and we're stripping it down. So it's just the simplest possible interaction. So the human gets one scalar decision variable, one continuous input, and the machine also gets one scalar input. So we're basically, the decision space is the XY plane, if you will, but I'm going to call it, H and M just to remind us what these two stand for. And we kind of carefully design these cost landscapes to have interesting properties about where the minima lie and how where the stationary points from their interaction, the game will lie and things like that. So if I look in this, XY plane of human action and machine action, then we design these cost functions so that, okay, the absolute best place from the human's perspective for the cost that we're prescribing to them is somewhere over here. And then similarly, the absolute best place for the machine is somewhere over here. But of course, they're playing a game. The human doesn't get to decide what the machine does, and the machine doesn't get to decide what the human does. And so other useful information to visualize are like the best response curves. So this is, the human accepts that the machine is going to do what the machine does. And so subject to whatever the machine's doing, the human's going to do the best thing it can for itself. And then similarly for the machine. Now we're choosing quadratic costs just to make things simple, in which case these best responses are lines, because they're obtained by taking derivative of cost, setting it equal to 0, so solving a linear equation. And what's really interesting is where these two intersect, because for folks that are familiar with this area, you already know that this is the Nash equilibrium of the game, which is, in this case, because we designed the landscapes carefully, very distinct from these global minima. And a natural hypothesis is maybe this is where the two will end up. In the one study I'm aware of that tries to apply these game theory concepts in motor control, that was the observation that when humans interact in a sensor motor game, that Nash equilibria is the kind of natural thing that emerges. But in the human machine case, that's what we're exploring and seeing in what cases that's true and what cases it doesn't. So the particular experiment we're doing, we prescribe how the machine adapts. We're just, we get full control. So we just decide it's doing gradient descent with some learning rate that we control. Of course, right now we have no idea what the human's doing. So they get kind of free reign. We just get to observe. And this is the outcome of this experiment. We're using this crowdsourced online platform to collect the data. We have people play this game. And you see, yeah, the outcomes, the distributions kind of look like they're around Nash, although it's interesting because they definitely look a little biased. I mean, definitely more than like this dashed line is definitely not the median of these distributions. It's definitely biased in one direction. Interestingly, it turns out the direction they're biased in is toward a different stationary point of the game. It's called a Stackelberg equilibrium. And the more rapidly the machine adapts, or the higher its learning rate, the closer the distributions get to that Stackelberg equilibrium. So Stackelberg arises when you have not a simultaneous play, but a leader-follower structure in your game. In this case, when the machine is learning quickly, it's effectively acting as the leader because it's kind of getting to where it wants to be very quickly. And then the human responds to that. And they kind of get to take advantage of it and end up at a place that's in general better for them, this kind of Stackelberg thing. And so in this picture, it's not just the global minimum, it's not just the Nash equilibrium that we need to pay attention to, it's also the Stackelberg. And then the final thought that I want to get across, and then I'll conclude, is that this emergence of this kind of leader-follower structure based on how quickly the machine is adapting or learning is super interesting because it gives us a lever to kind of model and then exploit the model of the human, the way the human's responding. If the human was just themselves doing gradient descent, which these results could not happen if they were just doing their own version of gradient descent based on their own cost, they would have to converge to Nash. That's theoretically known. But the fact that that's not what people are doing, they're taking into account how the machine responds to their choices, means that we get kind of an angle in where we can do something else. We can get to other kinds of equilibria. There's a notion of conjectural equilibria, which has to do with the machine, in this case, the machine building a model of the human that's consistent with the human's model of the machine, and vice versa. Or we can kind of steer things to other places, global minima for the machine, social optima, other kinds of things like that. So in a sequence of experiments that we're really excited to, we're close to being able to write up and start sharing with the community. We actually did this. We had the machine model the person, try to estimate a model of the person online, and then update its strategy in response to that. So now the model of the human is that they're approximately a linear function. The machine estimates that linear function and then synthesizes a new response. And that iterating that process seems to converge to this new type of equilibrium. And so this has given us a bunch of ideas. We have other kinds of schemes in the works to, again, manipulate the outcome in this sensor motor game. But I'm just really excited about this prospect of, really opening up the space of possible outcomes in these sensor motor games beyond just the Nash, essentially. So with that, I think I'm right at or slightly beyond time, and so I would just like to thank you for your time, acknowledge the contributions of all my wonderful collaborators and funding agencies, without which, of course, none of this work would be possible, and then just make a plug for my PhD student Mamoni Yamagami, who is phenomenal. She's on the job market now. You should absolutely hire her. And then student Ben Chasnov, who will be on the market in a year or so. So thank you so much for your time.
Thank you so much, Sam. That was great. Some questions. We have a question from Sam McDougall, who says, awesome talk. Do you think the hand transfer results suggest body independent, i.e. perceptual or cognitive learning?
It's an interesting question. Right, because I think we can directly infer that something, that's not specific to one or the other hand is being learned. I think the results kind of directly imply that in this context. But we haven't tested, other kinds of generalizations. So if I took this and then I hooked them up, for instance, to the muscle interface, would there be some appreciable, if I'm understanding the flavor of the question, one would ask, could there be some appreciable transfer between, fundamentally different modalities or different contexts or things like that? Yeah, I think I can't confirm that it suggests that. I think it's an interesting question, though.
Yeah, I mean, to some extent, you might consider that the sort of definition of non-motor learning, that it would generalize across effectors, but it depends what you like to call motor, I guess. Right. Paul Gribble, which I think maybe a similar question, says, to what extent do you think your result depends on the games being sensory motor? E.g., if the human responses were verbal instructions, left, right, would these patterns still occur? E.g., sensory motor versus cognitive task?
Yeah, great question. Yeah, so what is it that I'm trying to define to be a sensor motor game? Is what I'm inferring as part of the question. And a couple of key characteristics that are different from at least the example that was proposed of left, right, or categorical. One key thing to me about sensor motor is that the space of decision variables or actions is continuous, not discrete. So whereas Nash equilibrium, like a prisoner's dilemma or something like that, these kind of classical notions, bimatrix games and things like that, depend on the space of strategies, the space of actions being, left, right, up, down, or some set of numbers or options or something like that. Whereas what's a key thing about these sensor motor games is that they take place in this continuous space. And that means that we get a whole different suite of analysis tools and experimental tools to study them. So, Nash equilibrium in a pure Nash equilibrium in a discrete game is like, oh, I decide always in prisoner's dilemma to defect. But then there's also mixed strategies, which are kind of probabilistic things, and that's how you get kind of a continuous thing. But I think that you can get really natural continuous dynamics arising in sensor motor things where the decision spaces are continuous, and that distinguishes them in a way. Let me see if there's anything else I want to. Yeah, and then the other thing, we haven't done this yet, but that I hope to get to in terms of making this more sensor motor versus cognitive is, leveraging some of the findings and the techniques from the first half of the talk. So, eventually modeling not just, human kind of scalar response in a single cost landscape, but actually in a, human response. And we're doing experiments now to kind of probe this in a dynamic game where the person is choosing not just, one number on a continuum, but a whole control strategy, a whole, linear system that they're instantiating of board and feedback controller. And I think that could also distinguish sensor motor game versus other classic economic or cognitive games.
Great. Well, thanks very much, Sam. There were a couple more questions, which maybe you can address in the chat. In the interest of time, let's proceed to the next speaker.
Fantastic. Thank you so much for your time.
So can I just share the screen?
Oh, yeah. So, sorry. Our next speaker is Nobuhiro Hogura.
Yep. Can you hear me?
Yes. Yeah, we see your slides. Thanks.
Okay, fantastic. Okay, first of all, thank you very much for the organizers for running this fantastic meeting while in these difficult times. And the work today I'm presenting is all the heavy lifting is done by the first author, Kisho Ogasa, who was a former postdoc. And today I'm just going to explain what he has done in this couple of years. So the question I have is well, anyway, okay. So there could be a situation a player is kicking to the right after a very easy decision. You just have to kick to the right. So there could be another situation where the guy kicks to the right, but after a very difficult decision, maybe he was wondering whether he should kick to the left or not. So the question of this talk is, are these seemingly same action coded differently in the brain? How can I can't see all the slides. Okay, anyway. So in the motor areas, it has been shown that the stimulus uncertainty is coded. So do you know how I can kill the screen?
What do you mean?
So there's something on the top and I can't see the title of the slides, but anyway. Well, anyway, I'll continue, sorry. So in the motor areas, it has been shown that the uncertainty level is reflected. For example, in these like animal studies, when the monkeys are making decisions using their eye movement, the uncertainty or the difficulty of the decision is reflected in these cortical motor areas, the final output stage of the eye movement, frontal eye field. And also a similar thing is found in the hand movement also, and in the primary motor areas and those premotor areas, those activity in those areas reflect the uncertainty levels, okay? So activity pattern in the motor system reflects the state of uncertainty preceding the action. So a question is the action learned and memorized differently in the brain depending on the preceding decision uncertainty? So this is a task we set up. So participants grab the handle and look in the center, and there was a random dot motion coming out. And if the majority of dots are moving to the right, they grab the handle and then they move straight to the target on the right. If they think it's moving to the left, they grab they move the handle straight to the target to the left. So for this handle, or the manipulandum, a velocity-dependent force field is applied, and participants learn to make a straight movement of this force field. So we can vary the decision uncertainty level by changing the coherence levels of the random dot motion. If the coherence level is 100%, for example, going to the right, all the dots are moved to the right. So the decision is very easy, and it's in a very certain situation. On the other hand, if the coherence level is 3%, then the situation is very difficult to judge. So it's in a very, very uncertain situation. Okay, in the first experiment, we wanted to test whether the match between the coherence level, whether the match of the decision uncertainty level between learning and retrieve will influence the accurate recall of motor memory. Okay, so we have two groups of group of participants in the learning phase, and for the first group of participants, they learn the force field while after following the judgment of the certain visual stimulus, 100% coherent motion. The other group learned the force field following the decision of a very uncertain visual stimulus, a 3% coherence level. After they have completed the motor learning, there was a retrieval phase, and we varied the coherence level from 3% to 100%. Okay, and the retrieval or the recall of the memory was evaluated by the error clamp trials. Okay, so we have three hypotheses. Okay, so let's see. So this vertical axis, for example, is representing the amount of force they produced to resist to the force field, and this horizontal axis is the motion coherence level. Okay, so the red line is representing the subject learned the force field under the certain decision, and the blue is a group of participants learning the force field under uncertain decision. So if the decision and action are completely independent, so it doesn't matter what kind of decision state they learn the action. So they should always be good in making the action. So another possibility is that the performance is bad anyway when the decision is uncertain. So this is kind of a bit intuitive, right? So when you're like confident about moving, perhaps your performance is good, and you're anyway bad when your confidence is low for the decision. And the final hypothesis is the match of the decision uncertainty level between learning and retrieval phase is important for the accurate recall of action. Okay, so when you have learned the force field under a certain situation, when you encounter a certain situation, you can produce the force very well. But if you're in an uncertain situation, you can't recall it properly. And for the people who learned the force field under uncertain situation, the pattern would be opposite. Okay, so this is the result. Okay, so this is a result from the learning phase. The red is the people who learned the force field under certain situation, blue in uncertain situation, and this is the result of the error clamp trials. You can clearly see that both group of participants learn the force at the same level. Okay, so this indicates that uncertainty does not affect the learning of the force itself. And this is the result of the retrieval phase. Performance is clearly tuned to the uncertainty level of when the force was learned. Okay? So if I explain again, if you learn the force under a certain decision, you can produce the force very well, but if you're in the uncertain situation, the amount of force drops to 80%. And for the uncertain group, the result reverses. So the motor memory is tagged by the uncertainty level of decision prior to the action. So we had three hypotheses, and the third one was supported by the data. Okay. So in experiment one, we found that the motor memory is tagged by the uncertainty level of the decision prior to the action. And if this is true, then the people should be able to learn two different force fields if associated with two different decision uncertainty levels. And this is what we tested in experiment 2. So this is an experimental illustration. People made a decision for 100% coherent motion, and that was associated with a strong force field. And for the 3% coherent motion, it was associated with a weak force field. And after the learning was completed, they went into a retrieval phase where they had error clamp trials, and 100% coherent decision or the 3% coherent decision was presented. And we wanted to see what kind of force profile they would produce. So we have, again, two hypotheses. If the decision uncertainty cannot be a context for motor memory, they should not be able to differentiate these two force fields. So the amount of force they will produce in the retrieval phase will be same between the 3% decision and 100% coherent motion decision. Whereas if the decision uncertainty can be a context for the motor memory, then they can produce a stronger force for 100% coherent motion, a weaker force for the 3% coherent motion. Okay, let's go to the results. And this is a result when the strong force was associated with a certain context. You can clearly see that after the learning, the certain decisions, force field, the aeroclamp trials, after the certain decisions, you can see that there's a stronger force compared to the uncertain decision trials. And for the subject, which association was reversed, then the result reverses also. When the strong force was associated with the uncertain context, people produce more stronger force for the uncertain context compared to the certain context. Yeah. So this clearly means that a decision uncertainty context enables learning of two different actions. So again, we had two hypotheses here, and the second one was supported. So we had a couple of control conditions to exclude other possibilities, whether the visual appearance or stimulus duration can be also the cue for to learning the two different force fields. I won't go into detail, but in the control experiment 1, we tried to control for the visual appearance and the duration. In the control experiment 2, we tried to control for the amount of motor preparation. And this is the comparison. This is the result of the previous one, the previous main experiment. The difference between the two different force fields is you have a stronger one for the main experiment. For the other two control condition, it's much more smaller. So this result cannot only this result cannot only explained by these other confounders. So in experiment 2, we show that this like uncertain decisions or uncertainty of decisions can tag the different level of force fields. And next, we wanted to know whether this tag can transfer to the uncertainty matched situation of the different visual stimulus. Okay. So what does this mean? If this is true, we can say that the motor memory can be tagged with the uncertainty independent of the visual input features. So in experiment 3, we tried to do that. So first, we tried to match the uncertainty level across different visual stimuli. So we have this random dot motion where participants judge which direction the dots are moving. We have these arrow stimulus, which is a sequence of the arrow of left and right arrows. And after the sequence, participants has to judge which arrow is presented more in the sequence. Okay. So random dot motion, you can change the coherence level to change the uncertainty level. For this arrow stimulus, you can change the left-right ratio to change the uncertainty levels. Yes. So we want to find a equivalent uncertainty level between these two stimulus. And for that, we took the confidence ratings. Confidence is a subjective uncertainty. Okay, so this vertical axis is the confidence rating of the participants. The horizontal axis is the strength of strength of the stimulus. Okay, and the blue is the random dot motion. Red is the arrow stimulus. Okay, we first look into the random dot motion stimulus. If the random dot motion, the coherence level is 100%, the confidence rating is very high, and
5 minutes.
3% coherent motion, the confidence rate is very low. So we want to try to find the equivalent match in the arrow stimulus, and we found that 55%, 45% matches with 3% coherent motion, and 9-to-1 matches with the coherent motion 100%. Okay, so we want to do that. Okay, so I'll just go a bit quickly. Okay, so first, people learned two different force fields associated with the uncertainty of random dot motion. This is the same as experiment 2, 100% coherent motion associated with strong, weak, 3% coherent motion associated with weak force. And after the learning has been completed, we did the retrieval phase in the aeroclamp trials, but using the both stimuli. Okay, so random dot motion and the arrow stimulus. Note that the arrow stimulus, people have not experienced any force, so you can't really learn the force from the experience. So if the uncertainty in context is about the visual uncertainty, we should replicate the result of experiment 2 for the random dot motion. There should be no difference for the arrow stimulus. But if the uncertainty context is about the action or decision uncertainty, we should find the difference both in the random dot motion and the arrow stimulus, because they can share the confidence context. Okay. So I quickly go through. This is a result. So this is a replication of experiment 2. They can differentiate the force level depending on the uncertainty in context, and this transfers to the arrow stimulus. People produce a strong force for the certain arrow and uncertain weaker for the uncertain arrow, and half of the participant is opposite. Okay, so this hypothesis was supported. So I hope I could have convinced you that the decision uncertainty can work as a context for motor memory. So parameters directly involved in motor planning control have been shown to work as a context for motor memory. But in our experiment, people are like making a straight movement to the target in both situations. So what we want to say here is that this latent internal state of decision can work as a context for motor memory. Okay, and the action following certain and uncertain decisions are coded differently. Thank you very much.
You're muted.
Thank you very much for that talk. We have time for questions. All right. So Rich Ivory asks, for experiment 1, an alternative to the tagging hypothesis is that there is a cost when you experience a novel context, and and it is surprise rather than similarity that leads to reduction in force or recall. Both groups show a drop associated with the level of novelty. Any thoughts on this alternative?
Yeah, so yeah, that can be certainly a confounder for the experiment 1. So yeah, so one context is they experience a lot. One uncertainty context they experience a lot, the other not. So the tuning can be confounded with that also. But I think the experiment 2 and 3 backed up with an initial hypothesis of tagging by uncertainty.
Okay. I have a sort of this little sort of simple question. Yep. I guess I had trouble understanding the units that you're using to describe the amounts of learning. I mean, there were
right.
There were numbers like 0.00.
Oh, right. Sorry. So that is like a force divided by the velocity. So the expected value, the full value is 0.01. So it's like, yeah. So it's a bit complicated, but.
Oh, I see. So the velocity is like a millimeter per second or something. So normally, for most sort of normal first fit learning, that those values are something like 15 or 10 or 12 or something. But
yeah, so
it depends what units you're using.
Yeah. So basically so in this case, 0.01 is the fully compensating for the force here.
Okay. Yeah. All right. So we multiply this by 1,000.
Yeah.
All right. Okay. Alkas Haji-Yosef asks, it seems coherence can act as a retrieval cue for force field strength when the force field points in the same direction in both cases. Do you think one could be able to teach opposing force fields based on coherence?
Okay. So in our particular case, so I think you're talking about the reason why we use the strong force and the weak force.
So you strong and weak.
Compared to the conflicting force. Initially we were using quite a strong like a conflicting force, and the participants, a couple of participants, we tried 1 or 2 and they just simply gave up in between because it was too difficult. So we just changed to a slightly easier situation. So but but the good thing about the current situation is I think the explicit strategy cannot not be strongly used, and also I think conceptually it's not that big difference between the strong and weak compared to the conflicting force. I'm not fully sure, but yeah.
Okay, so I guess related to both your answer there and to my other question, I guess I had a little bit of trouble appreciating, like you showed, looked like to me like quite clear results that for this, I guess, success second experiment, we have strong and weak forces, and the tagging that the motor responses were really distinct, right? According to this strong weak, but I had trouble sort of understanding from that one, just how close each of those responses were to the ideal, and more specifically, like what was the ratio of the sort of the force field compensation levels to the ratio of the ideal, of the force fields to which they're exposed to for strong and weak. So I'm asking, that it was clear that experiment like qualitatively worked. I guess I just want to know quantitatively how well did people?
Yeah, so the full force is if you fully compensate, it's 0.01 and 0.005. Okay, right. So it's so in that sense it's compensating for like 60% of the actual force. I think 70%, not 60, but 60, yeah, around 50-60% of the actual force, and it still differentiates. Yeah, is that answering the question? Or?
Okay, so in general, like the one with the stronger force field is actually more appropriate for the weaker force field, but it's still stronger.
Yeah. Closing. Yeah.
I see. All right. All right. Well, thank you very much. Really appreciate it. That.
Thank you very much.
We can move on to the next talk, which is from Day2, who works with Adrian Haith, and his talk is titled "Dissociable Habits of Response Preparation and Response Initiation."
All right. Okay. Can someone confirm you can see my slide and hear me? All right. Great. So today I'm going to talk about dissociable habits of response preparation and response initiation. So first, what is habit, right? Without defining what habit it is, then we all claim that we have some habits in our daily life. For example, we follow certain life routines in everyday activity. We like drinking coffee or eating chocolate when writing a paper or writing a grant. Right? And some people may be addicted to alcohol or smoking, and others may have some compulsive behaviors. And all of those are related to habit. But today we're going to focus on one particular type of habit, and which we think is very much close to a motor skill. It is called slips of action. Imagine a scenario that someday you want to open your phone and order a cup of coffee through your phone, and open a Google map when you're driving, right? What you're going to do is pull out the phone, unlock it, and very easily tap the icon you need without much thinking, right? This action can be explained by automatic stimulus response association. But sometimes this association can give us trouble because the response can be automatically triggered even though it is no longer wanted. So for example, one day you decide to reorganize the icon configuration on your phone. And when you, after that, when you try to order a cup of coffee, open a Google map when you're driving on your phone, occasionally what's gonna happen is you habitually tap the location where the icon was located before. Okay, so the mistake like this, slippers of action, can cause these small mistakes, but sometimes can cause very much worse consequence. For example, when you're playing sports game, when you're driving a car on highway, or when you operate a robot, a surgical robot. Okay, so to study slippers of action, what the task we used is called arbitrary visual motor association, where you learn to associate a set of stimuli to a set of responses. So here, each stimulus is associated with one particular response. So you can imagine after you practice this particular association for a long time, then you're supposed to become habitual on this association. which means the presentation of one of this particular stimulus will automatically trigger its associated response. Okay, so to examine whether we actually become habitual on this association, there are two methods. One is that we can revise the association between the symbols and the responses. So if you become habitual on the original one, you are going to, when you see this particular symbol, you are going to use the original response instead of the newly acquired one. Right. Using this remapping paradigm, Hardwick and colleagues found a very strong evidence of slips of action in human participants in their 2019 study. Alternatively, the other way to tackle slips of action is that people instruct participants to withhold the response to some of those stimuli. Right. Similarly, if you become habitual on the original association, the presentation of this particular symbol will automatically trigger the originally associated response. However, now the stimulus does not require that response anymore. Okay. Unlike remapping paradigm, responding withholding paradigm, there's no much success in demonstrating slips of action in human participants. Okay. A good example is by the study by DeWitt and colleagues, where they did use 5 variants of the withholding paradigm, and none of them demonstrated slips of action in human participants. Okay. So what is the reason behind the conflict results that we observe slips of action under remapping paradigm, but not under the withholding paradigm? Right. One simple explanation is there are some methodological discrepancy between these two paradigms. For example, in Hardwick's study, people has a lot of trials of practice on the original association. And when probing habits, they are forced to respond very quickly. And also the way they revise the stimulus response association is by changing the association directly. However, in DeWitt's study or in withholding paradigm in general, people often has much less trials of practice and the response is very slow. And also the way they revise the stimulus response association is indirectly through evaluating the outcome of some responses. Okay, so this might be an explanation why we observe conflict results between these two paradigms. However, another possibility is that these two paradigms actually tackle different components of action control. So Hardwick's study already suggests that the remapping paradigm probe habitual response preparation, because when people being forced to respond as quickly as they can, the only decision they need to do is what response to choose, because they are forced to choose the response at every single trial, even though by guessing. However, additional component involved in withholding paradigm is we need to make a decision about whether should we initiate a response. Okay, so these two papers at the bottom of this page already highlight the independence between response preparation and response initiation. So it's reasonable to think that the habit of these two components can be dissociable. So to differentiate these two possibilities or hypotheses, we are going to directly compare these two paradigms by using the same volume practice and forcing people to respond rapidly and by changing the stimulus response directly. Okay, if we observe slips of action in both approaches, it may suggest these two paradigms actually tackle on the same phenomenon of the same type of slips of action. However, if we observe slips of action in the remapping condition, but not the withholding approach, it might suggest that these two approaches tackle on dissociable slips of action, especially about habitual preparation and habitual initiation. Okay, so in experiment 1, we used arbitrary visual mode association between A symbols and 4 responses. And the reason we use A symbols instead of 4 is we want to make sure that every response is still required in the withholding group, because otherwise people may adopt a smart strategy to totally shut off some response to avoid the habit. Okay. So importantly, these two groups participants follow exactly the same procedure where they learn, practice, and being measured on the original association. And afterwards, they learn the revised association before we probe a habit. And all of these blocks use different tasks. Here we're going to focus on the most important one that we use to probe habits and measure the practice effect on the original association. It is called the forced response time task. In this task, people need to respond at a certain time point by synchronizing with some external signal. And we can manipulate in the onset of the stimulus presentation relative to the time of response. so that we can force people to make a decision at a different response time, available response time. So in this way, we can measure that which response people choose at each of those individual manipulated response time. And using that discrete measurement, we can construct the speed axis trade-off of each type of response to one particular symbol. For example, the blue curve here shows that the correct response to this particular symbol gradually increase with longer response time. But the probability of choosing the other three random errors decreased with the longer response time. And similarly, we can construct the probability of response and no response in the withholding paradigm as well. Okay, so before we probe habits, we simply go over the practice results and make sure that these two groups has comparable performance and the similar practice effect before we probe habits. And the results confirm so because they have a similar amount of increasing accuracy, reaction time, and they also show the similar improvement regarding the speed axis trade-off on the original association. In addition, people do not have difficulty to learn the revised association, even though they practiced like about 1,000 trials on the original association. And this learning ability is comparable between this remapping and withholding group, revealing by the number of trials they need to learn the revised association, which is the right bar on each of this panel. Okay, so this is the most important results we want to discuss. It's about the habit. So let's look at the remapping group first. There are two types of stimuli on the remapping group. One is the unchanged stimulus, which is always associated with the same response between the original and the revised association. And the other one is the revised stimulus, which is associated with different responses between those two associations. So there are two kinds of response to the unchanged stimulus. One is the correct response, and the other one is the other three random errors, as we showed before. So if people are able to perform this time response task, we would expect that they start from a chance level by picking one of these choices randomly when they have a very short response time. But with longer response time, we would expect the probability of choosing the correct response gradually increase, and the probability of choosing the other three random errors gradually decrease with longer response time. And this is confirmed by the results, suggesting that people do not have difficulty performing this time response task. And using this speed axis trade-off here, we can also determine the minimum time at which people become able to process the stimulus and be able to choose an action rather than randomly guessing at the baseline level. And using this minimum time, we adjusted the temporal profile of the responses to the revised stimulus before we examine habits. And there are three types of response to the revised stimulus. One is the correct response according to the revised association they learn. And the other one is that sometimes they may randomly choose the other two keys, which are never associated with the revised stimulus in either the original and the revised association. Most importantly, the last type of response they can choose, we call this habitual response, which is according to the original association they have a lot of practice on. And the inference of habitual preparation in this remapping paradigm is the higher probability of choosing the habitual response compared to the lower probability of choosing the other two random responses. Okay, another way to understand this is that after we become able to choose the right action, which is the blue line, whether the probability of choosing the habitual response is higher than the chance level, which is one of the third keys they can choose. Okay, so both of these methods confirm that there's a habitual preparation under the remapping paradigm, which replicates what has been observed in Hardwick and colleagues' study in 2019. So what about withholding group? Right. There are also two types of stimuli, one unchanged, the other one is revised stimuli. And to both of these stimuli, there are two types of response. One is the initiated response. The other one is they do not initiate a response at all. So the summation of these two curves should be equal to 1. Okay, and we use this probability curve to establish a baseline where people randomly guess whether they should initiate a response. And we're going to use this baseline to infer habitual initiation. So again, there are two types of response to the the revised stimulus again. The first one is whether they correctly withhold the response according to the revised association they learn. And the other one is they habitually initiate the response, even though the stimulus does not require one right now. So because the probability is always lower than the baseline chance level, so there's no habitual initiation with respect to this arbitrary visual motor association they learn. But importantly, if we decompose this probability of initiation response to initiate the original response to initiate the other three random response, we found that even though people do not habitually initiate response, they do habitually prepare the originally associated response to this particular revised stimulus. So taken together, the results from experiment 1 suggested that there's the habitual preparation. Thanks. There's habitual preparation under remapping condition, but even though they habitually prepare the response, they do not habitually initiate it, okay? Even though they are forced to make the weather decision rapidly. So the results suggest the mechanistic explanation why we observe different results under these two paradigms. And it suggests that the remapping and withholding paradigm actually tackle dissociable slips of action. So now the question remaining here is that can response initiation become habitual, right? One answer is probably never can become habitual. And the other possibility is that it may be, but it may require extensive practice. So one possible manipulation we can do on experiment 2 is that we increase the volume of practice on the arbitrary visual motor association to tackle habitual initiation. However, one problem is that there's uncertainty about how much practice is enough. Okay, so there's some risk to perform the experiment and without observing habitual initiation. So instead, we use a non-arbitrary visual motor association, which is supposed to be well learned through life experience, because we expect that people already associate with the numbers and the letters with the 4 responses in a rank order. Okay, so in experiment 2, we're going to use this particular non-arbitrary visual motor association, replicate experiment 1 by following the exact same procedure. Okay. First, simply let's confirm that this two group has the similar performance level before we prove a habit. Okay, and it's revealed by the number of trials they need to learn the revised association. And most importantly, there's no practice effect at all revealed by the constant accuracy, reaction time, and the similar speed action trade-off before and after practice, which confirms that this association is indeed well learned. So the habit under the remapping group showed a very similar picture as we observed before in experiment 1, except that the probability of choosing the habitual response is a little bit higher than experiment 1. Okay. And we also show a similar picture to the response to the unchanged stimulus under the withholding group. Okay. But the picture of the response to the revised stimulus showed a completely different picture, because specifically, if you look at the probability of initiating a response, they start from a chance level, which by random guessing whether they should initiate a response when they have a very short response time. But this probability increase above chance when they have a relatively longer response time to make the decision. And the probability keep decrease towards 0 when they have longer enough response time to make the correct withholding decision. And this results shows that initiation becomes habitual under the non-arbitrary visual model well-learned association. And again, we show that whenever they initiate a response, most time they initiate the originally associated response rather than the other 3 random responses. So by summarized results, we directly compare the 2 figures between these 2 experiments. So we show that there's no habitual initiation to the arbitrary visual model association, even though after 1,000 trial practice, but initiation indeed become habitual to the non-arbitrary visual model association, which is supposed to be well learned in real life experience. Okay, so by these results, there are a few takeaways we want to give. So we argue that the remapping and the withholding approach do not assess the same type of slips of action. Instead, they measure qualitatively distinct type of habits, which are related to preparation and initiation. And these two independent components of action control, preparation and initiation, are found to be able to become habitual, but depending on different time scales of practice. And the last and the most important message you want to deliver today is that beyond the preparation and the initiation, we argue that any component of action control can potentially become habitual. So in the future study, when we consider habit, we should consider the individual qualitatively distinct component of action control rather than consider the response as a whole as a habit. Okay. And finally, I want to thank all my colleagues, former and current lab mates, who gave me constructive comments on this particular study and presentation. And now I welcome any comments and questions.
All right, well, thank you for the very nice talk. Leah and Adrian, I'm having some technical difficulties here. For some reason, like I can't get the questions to come up on my Zoom screen here. Is it possible one of you guys could step in? Or I don't know why I'm not seeing them.
I could do that. Just a second. I'm trying to. Oh, there are no open questions yet. Does the audience have any? So I have a question. As I sort my view here. So I guess my question is, why do you think there is a difference between preparation and initiation? Why does the habitual development there require extended practice?
So your question is why habitual initiation require extensive?
Right, why, yeah.
Well, we think if we consider preparation and initiation as independent, right? We can improve the speed of making the decision about whether we should initiate response by practice. And once we have that decision can be made rapidly, and then you revise the requirement. And if that decision is habitually pops up when you were forced to respond rapidly, then it probably shows the habitual initiation. So that's why, so the practice actually improve the speed you make the decision about whether you initiate response. And that faster speed can cause some trouble if sometimes the task requirement change.
All right.
Okay, sorry, I see.
Want to jump in, Maurice?
Yeah, sure. There is a question from Ryan Moorhead, who asks, do you think it's the case that cognitive control can override any habit at higher reaction times, at least for humans?
You mean longer reaction time? I mean, if the higher reaction time is longer reaction time, yes. I mean, by delaying the time when you make the decision. So which is showed in the learning block. Actually, if we instruct them to respond as slow as they can, they do not have trouble to perform the task at all. So the habits only shows when they are forced to respond rapidly. But if the higher reaction time means lower reaction time, so I'm kind of confusing here, then I don't think we can overcome habit by some cognitive control if we need to respond very quickly.
Okay,
that's my opinion.
Rich Ivory has a comment and a question. His comment is it seems to tie in nicely with Tim Carroll's talk on subcortical control of movement. And his question is, are the reaction time distributions similar in the prep and initiation, despite the forced RT method?
That's a very good question. Actually, we have some, I'll show you some data here. So when people are instructed to go as slow as they can and maximize the accuracy when they learn in the association, actually the response time is longer in the remapping condition than the withholding condition across these two experiments. So if you look at this bar, the remapping, which is higher than this bar, which is withholding in experiment 1, and this is longer response time in remapping and shorter response time withholding. And also, when we force them to respond rapidly, we also observe kind of different time response distribution. Here we show you the minimum time where they become able to decide whether to make a decision or which response to make. And in general, there's a trend that the response time in remapping is a little bit longer than the response time in withholding between in both of these two experiments. Yeah. So my guess is that the decision about whether happens earlier than the decision about which action to produce. But this is not conclusive. It's just a preliminary results about the reaction time.
Okay, so one final quick question. Abigail Person asks, have you thought about looking at these processes in children to see if the habitual initiation is easier to extinguish than in adults?
That's a very great question, actually. So yes, if we think children learn more implicitly than adults, then it's more easily for them to form habits than adults. But about talking about the extinguishment of habits, we don't have idea, because I think the general hypothesis is if they have a stronger habit, it's harder to extinguish. So that should be harder to extinguish habits in children than adults.
All right, thanks a bunch, you. Appreciate it.
Thanks.
All right, so our final talk before the break, for a 10-minute break, is from John Pickovents, and his talk is titled "Explicit Changes in Movement Planning in Response to Stop Signal Uncertainty."
Hi there, thanks for the introduction. Can you just confirm that you can see and hear me loud and clear?
Yes, absolutely.
Thank you very much. Okay, and thank you all for attending this talk where I can showcase the work we've been doing. So if I said baseball, I expect something like this would spring to mind, right? Ichiro Suzuki under lights swinging for a home run. And it's not just because it looks cool. This is a motor control conference. We're interested in movement. So how we plan and execute accurately timed swings, these kind of questions interest us. But in baseball, not only do you have to be able to plan and execute an accurately timed swing, your success is also predicated on being able to withhold that movement in response to an errant pitch to avoid striking out, which isn't what springs to mind, but perhaps it should. We're interested in movement. Under those conditions, how does that affect our movement planning? So in the inhibition literature, people often reduce movement to single button presses. So they're only really interested in the effects of uncertainty over withholding movement on the when of initiation time. But we're in this study combining timed interception with stop signal paradigms to investigate the effects not only on when the initiation is timed, but also how the movement proceeds. So we do that with this task, Fruit Bat Splat, which is a task that we programmed in Unity and is implemented through WebGL. So you can do it in browser. There's a link here if you'd like to try the demo. Don't worry, it's really short. And also, you know, by all means, check out some of the other work we've been doing in the lab, which might be even more interesting. This is what the task looks like. We've got a target in the top left-hand corner, an unidentified fruity object. And then, just like in baseball, in the bottom right-hand corner, we've got a bat. And this is controlled by the mouse or trackpad of the user. Unlike in baseball, we fixed the movement path of the target and the bat in the X and Y axes, respectively. This is to allow us to fix the interception point. So we're not concerned about where they're trying to hit it. That's fixed. We can just look at the timing aspects of the movement. So at night time, it's safe to leave the cave. This is when bats like to hunt for fruit. So when the participant's ready, the target's going to appear in the corner, and after a random delay up to 500 milliseconds, it's going to move across the screen. Participants are instructed to leave the cave and try and strike it with a ballistic movement, sticking trained to move between 100 and 300 milliseconds prior. And also the movement's been calibrated to get some kind of control over this online. And so in this paradigm, not only do we know when the bat leaves the cave, the initiation time, but we also have a movement time. So the time it takes from the bat to get from the cave to the interceptive point, and the timing error associated with that. So if the bat strikes the target through the center, that's a 0 timing error. But then if the target's past the interceptive point, the bat arrives late, which is a timing error greater than 0, or if it arrives before, that's a timing error less than 0, so the bat arrives early. So just to note, because there's the thickness to the target and the bat, it's possible to hit the target with a non-zero timing error. So for this particular experiment, the timing window, how long the target took to cross that point, was about 300 milliseconds. So as long as they arrive within 150 milliseconds either side, they will hit the target. So that's at night time. Now at dawn, it's also safe for fruit bats to go out and hit the fruit. So when they're ready, it's going to appear. After about 5 milliseconds, it's going to move, and they've been trained to try and hit the target with a ballistic movement. Same again. But because it's dawn, the sun might also rise spontaneously, and this is our stop signal. If the bat is outside the cave, when the sun comes out, it's going to get burnt to a crisp. And we introduce this at a time before the movement's initiated, but after it's begun to be prepared. So if we take a closer look, enhance. This is how this has been looked at in the stop signal paradigm. So traditionally, a stimulus is presented, and this generates a go process, which begins to accumulate towards threshold. In ours, this go process begins to accumulate when the target crosses a point equal to the time taken that we've estimated it's going to take us to move to the interceptive point, plus the delay associated with this signal. And so as it moves closer, the signal gets closer to the threshold, but then prior to movement initiation, we might introduce a stop signal. It changes to daytime. At this point, the stop process begins to accumulate, and whichever of these two processes wins out predicates the outcome. In this case, the bat leaves the cave and is burnt in the sun. If on the next stop trial, we present the stop signal earlier, once again, the go signal begins to accumulate when the target crosses the point at which we'd estimated our movement is going to take to get to the interceptive point, plus the delay associated with this. But the stop signal might come in earlier. And in that case, the stop signal might reach threshold sooner than the go signal, in which case we successfully inhibit our movement, which is described here in the safe graphic. Now, whether or not participants inhibit their movement is going to depend on two things. It's going to depend on how late the stop signal is presented and how quickly the stop process finishes. Well, this is the stop signal reaction time, which is the primary measure of reactive inhibition. Now, we control experimentally the stop signal delay. So on incorrect initiations on stop trials, we bring the next stop signal delay 50 milliseconds forwards. And when they successfully inhibit, we push it back 50 milliseconds. So over the course of the experiment, we track to get to a point where approximately 50% of the time participants will successfully inhibit their movement. The only other thing thing that predicates the outcome is a stop signal reaction time, which is an automatic and reactive process. Participants don't have any control over, and because we're controlling the stop signal delay, it's almost as if they can't influence the outcome here. They can't increase their odds of inhibiting, but that's not strictly true, because something that we observe, if we go back to the case where the go signal outrages the stop signal, is that participants artificially delay when their go signal begins to accumulate. So given the same stop signal delay and the same SSRT, you can artificially inflate the amount of times that you successfully inhibit. But what does that mean for those trials on which a stop signal isn't presented? Well, it means that we delay our initiation. And this is what they find in these simple button pressing tasks. When on the uncertainty of a stop signal, people delay their movement initiation relative to conditions where there isn't a stop signal presented. But what does that mean for our movements, which is more than just a binary act or not? Well, the purple line here represents when the center of the target would reach the fixed interceptive point. And so from when the target moves to that point, this is how I'm going to define initiation time. There's the time to contact of the target to the center of the interceptive point when the bat moves. And if we move at a movement time that's equal to that time, then we're going to strike the target perfectly through the center with a timing error of 0. But in the case that we delay our initiation, what's going to happen? If we move at the same movement time, we're going to arrive later at the target. But actually, in these timed interceptive paradigms where you fix the interceptive point, what you tend to find is when people delay their initiation, it corresponds to a briefing of the movement time, such that the timing error is preserved. So perhaps in our task, what we'd expect in dawn conditions relative to night conditions is that participants would move later in dawn conditions with briefer movement times. And so we ran this experiment on Prolific with 50 participants, and this is how we blocked it. We've got 2 conditions: certain condition, they're all going to be go trials, and an uncertain condition where 33% of the time we're going to present this stop signal. And there were 8 blocks of 30 trials for 240 trials in total. So here are the results. Here are just 2 kinematic traces comparing certain representative conditions to certain and uncertain conditions. And we can see that qualitatively, people seem to be, as we predicted, delaying their initiation. Now, the way this progresses over the course of the experiment, we found was non-linear. And so the dots here represent means at each trial of the 50 participants. And the lines are actually 3-parameter asymptote models that we fitted to better account for the non-linearity of the data. We didn't just want to take a simple mean. We thought this would kind of give us a more precise estimate. But all that's to say is that in uncertain relative to certain conditions, at the beginning and end of the experiment, people were delaying their initiation time. And it appears to be a greater effect in the uncertain condition over the course of the experiment. Now, for those who prefer means, we've, you can see those there with the dotted lines. And so, yeah, we get exactly the same result, plus or minus a bit of noise. As far as the movement time changes go, it's important to note that in these interceptive tasks, people tend to be moving at max velocity at the moment they cross the interceptive point. This reduces the error, and that's exactly what we observed in our task. So the time difference between initiation and max velocity tends to be when the bat reaches the interceptive point. You can see once again, qualitatively, between certain and uncertain conditions, people are moving briefer in the uncertain condition, which is also when they're delaying their initiation. And once again, over the course of the experiment, this is a non-linear kind of decay. And we show here quantitatively that in uncertain relative to certain conditions, people are moving briefer, both at the beginning and at the end, but that there isn't much difference in the magnitude of this effect. And in terms of the timing error, what we found kind of surprised us a bit, and that was that people were arriving later to the target in uncertain relative to certain conditions. And once again, it was a non-linear kind of progression over the course of the experiment. And here are the estimates from the parameters of the model and the means for the first block and the last block. The differences are at the start and at the end of the experiment, and they're much greater by the end. So if we just kind of reduce all this into a single plot to look at the effects of uncertainty of whether we're going to have to withhold the movement on this timed interception context, we can see that there are changes to initiation time. People delay their initiation. And this corresponds to a briefing of the movement time, which is what we predicted. But it's not so much that it accounts for, it can preserve the timing error. And so not only are people delaying their initiation, they're delaying their arrival. And that's the same at the start and the end of the experiment, to a greater degree. Now, this proactive, these kind of proactive changes to the movements in the simple button presses have always been assumed to be volitional, governed by explicit kind of conscious processes. It's a strategy that we employ, but it's never been tested directly. One benefit of our task is that we can represent these timing characteristics spatially. So for example, here, because the target moves at the same speed in both conditions, I've been able to convert when the bat arrives at the target into a where on the target the bat arrives, if that makes sense. So in certain conditions, the bat always arrives in the front half of the target throughout the course of the experiment. But in the uncertain conditions, while at the beginning of the experiment, the bat's arriving in the front half, by the end, it's drifted towards the back. And similarly, we can express when we initiate spatially in terms of how far the target's traveled across the screen when participants begin to move. And so to assess whether we have kind of explicit awareness of this, to assess whether, which would be the case if it was a volitional strategy, we assayed this at the end of the experiment. So participants observed a blank trial, and then were asked to drag the UFO to the point it was when they tried to leave the cave. That was both in the night and the dawn conditions, counterbalanced, just to be sure. And what we found here the crosses represent individual participants, the dots represent the overall mean, and the error bars are the confidence intervals adjusted for within participant comparisons. The people were indeed explicitly aware of their delay to initiation. And similarly, we asked them where on the bat they were trying to hit the target, where on the target they were trying to hit with the bat at night and at dawn. And once again, we found participants were aware of trying to aim further to the back of the target, although not in the white. It should be mentioned here, the ends 49, we had to throw one of them out. Online experiments, it's a hard life. I think their computer must have crashed or something. So taken together, if we look at the magnitude of these effects in the where people are reporting, we can see that people report a greater effect on the delay and in the initiation. So the target's moved further relative to how much further back they're moving on the target. And this correlates obviously with what we observed, right? People were delaying their initiations more than they were arriving later, because they were briefing their movement times. Another interesting aspect of this is that these reports are obviously smaller in size than the effects that we observed. And this could be for a number of reasons. So one is that it's, this is happening after they've done the task. So we're probing their explicit recall of the strategy. Maybe there's some kind of decay associated with the memory of what they were doing. Maybe there's some kind of weird demand characteristic where, they want to say that they were just striking for the center of the target every time. Perhaps more interestingly, maybe this, maybe there is, this is governed by explicit processes, but not entirely. Perhaps there's some kind of level of implicit adaptation that people are making in terms of where they're aiming and on the target and when they're initiating. These are obviously open questions, but for the first time, we've been able to quantify the effects of volitional proactive inhibition. So in summary, we combined timed interception and stop signal paradigms to get a richer picture of proactive inhibition, and we found that in response to the uncertainty of whether to withhold a movement, participants delayed their initiation and briefened their movement time, but not so much that they were able to preserve their timing error. And so this delayed initiation and delayed arrival, we were able to quantify in terms of how aware people were of this process, and indeed they were. And to the even though these effect sizes were smaller than the ones we observed, the relative effect sizes correlated perfectly. I'd like to thank you all for watching me mumble through this talk, and I'd be very happy to answer all of your questions. Thank you very much.
All right, thanks a bunch. That was great. I have a quick question of my own first.
Yeah.
So I found it sort of curious. I think relatively earlier in the talk when you showed the data in the certain case, and you showed that the population was arriving like 100 milliseconds early on average, or something like that.
This one.
Yeah. So the timing, right? That there is a sort of persistent sort of timing error.
Yeah.
In the certain case.
Yeah.
And so I just wonder, is there perhaps just like a, just maybe like a bias in your data from the just from the sort of like the inherent sort of system delays in presenting information on people's screens somehow, right?
Okay.
So, and really everything should be shifted up by 80 milliseconds or 100 or something like this.
I mean, that could be the case. I think there's a much simpler explanation for that. And that is, remember, they can still arrive 100 milliseconds early and hit the target, right? Because the target's present in the window for 300 milliseconds. And actually what you'd expect in these kind of interceptive tasks is for people to arrive earlier. Because if you think about it, if you arrive early, then you have the opportunity to correct that and still hit the target. Whereas if you arrive late, it's gone, right? So I think it's more reflective of that, which is something that is observed over and again in these kind of paradigms, rather than some kind of bias in my data. I'm not saying there isn't a bias in my data, but it doesn't surprise me, I guess, is my response to that question.
Right. So I mean, one thing you could do just to be careful is, run the task yourself or on a couple of different computers, right? And then the video record the screen.
Oh,
right?
you want to assess the lag.
The point is going to be there's some system lag, right, between when you actually sort of make responses and the computer records them, and when the display on the screen sort of shows up, and it'd be good to know what they are.
Yeah, I agree.
Class is really time independent.
I think experientially I can answer that question, and you can answer it for yourself too by following the link that I posted and feel for yourself what it's like. I haven't measured it, but I'd be very surprised if it was of the order of hundreds of milliseconds. And I'd also be very surprised, people adapt to it. Maybe that's why there is a curve here, a slight curve in the certain condition. But yeah, I don't think it'd be the order of hundreds of milliseconds. But it's certainly something we're looking. It's certainly something we're looking at in the lab, because we do we're doing a lot of online tasks in Unity, and yeah.
I mean, like in Tianhe's presentation yesterday, he tried to measure it and got something like 100 milliseconds, 120 milliseconds, I think. So,
oh really? What was he using? Sorry, I missed it.
Yeah, I don't remember the system. But okay, next question. Jordan Taylor asked, what do you think would happen if you required precision in interception? Would it seem that delayed initiation would result in more variability due to signal-dependent noise, and they had to aim to a different point on the target to catch up, then it could miss the target area. Perhaps this is what batters do when they are purposely hit a foul on a 2-strike count, so as not to strike out.
Yeah. So it's a long question. Let me break it down. So I think the first thing to say about signal-dependent noise is actually there's less variability in these tasks associated with delaying your initiation and moving faster than if you move slower, because it's a moving target. And if we move faster, we get a more accurate. So for example, you minimize you cover a much greater distance, right, in the same amount of time. So you minimize the error actually by moving faster and moving later. And which is like the opposite of what we see in like reaching and things like this. So I'm sorry, I forget the full question, but that was my response to part of it. What was the second part?
Well, I mean, I think that was the gist of it. He's just sort of just giving a reason to believe that. We have other questions, so I'll go on. Jonathan Say writes, very cool data. Can the slowing effect of uncertainty be predicted by the reward or vigor in the framework proposed by Ahmed and Shadmir? The high cost of potentially being incinerated in the uncertain condition may discourage people from moving more vigorously.
Yeah, no, it's a really good point. We haven't modeled this data computationally in that way. But obviously there's lots of sources of feedback that you get between trials, not only, whether you get burnt or not, but whether you miss the target or not. And, what are people favoring? Are they favoring hitting targets, or are they favoring not getting burnt? I mean, it turns out they're favoring hitting the targets because the tracking procedure works and people are failing to inhibit 50% of the time. But I agree, if we could look at the trial by trial variations based on those outcomes and see how that affects these rates and these changes for sure. And I think it would. And you could go even further. You could start assigning points. I like gamifying the experiments. You could assign points and see if that can kind of adjust the equilibrium somehow. It's definitely something down the line. It's just something, we haven't looked at yet.
All right, thank you very much.
Thank you.
So for everybody, we're going to take a 10-minute break before the next talks, and we'll see you back then. Yes. Fantastic.
You will tell me when can I start it. Yes.
Yeah. All right, everyone. Well, welcome back to the second session of the second day. So our final session. So to get us kicked off, we have Sharon Israeli, and he'll be talking about how blocking cerebellar signals increases internal noise and impairs motor adaptation.
Hello, everybody. I want to thank you for providing me the opportunity to present my work here. I'm Sharon Israeli, a postdoc in the Hebrew University of Jerusalem. My project aims to analyze the role of the cerebellum in motor adaptation in monkeys. The cerebellum is considered to have a major role in movement control and in motor adaptation. As such, damage to the cerebellum impairs the ability to predict and produce motor commands in given dynamics. Bastian and colleagues in 1996 illustrated a lack of shoulder-elbow synchrony as indicated by the sharp break in joint movement curvature. Cerebellar patients also demonstrated delayed latency of elbow movement relative to control participants. Cerebellar damage also interferes with motor adaptation, as was shown by Gibo and colleagues in 2013, who demonstrated significant increase in endpoint errors in patients with cerebellar ataxia, as the red line indicates, compared to control participants, as the green line indicates. This is a schematic illustration of the cerebello-thalamocortical system. It originates in the deep cerebellar nuclei, primarily in the dentate nucleus. It makes synaptic contacts with the cerebellar receiving areas of the motor thalamus and terminates in the motor cortex. In our lab, we use a stimulating electrode located at superior cerebellar peduncle to study the role of the cerebellum in shaping motor outputs. Through the stimulating electrode, we deliver either single pulse stimulation at low frequency, which aims to activate the system, or high frequency stimulation, namely HFS at 130 Hertz, aiming to suppress the cerebellar output to the motor cortex. In previous studies, we have already illustrated that HFS increases the curvature of hand pass, as you can see here, and changes movement parameters such as increased reaction time and movement time, and a decrease in movement velocity. Furthermore, as shown by the red trace, high-frequency stimulation significantly decreases the cortical response to stimulation compared to the response to the same stimulation when delivered at low frequency, as shown by the black trace. Here, PSTH traces were aligned on stimulation time. In the current experiment, we use the same settings to study the effect of high-frequency stimulation on motor adaptation. 2 monkeys were trained to perform a planar shoulder-elbow reaching task. In this task, the monkey were instructed to locate a cursor within the central target. After 500 to 800 milliseconds, 1 of 8 peripheral targets appeared. The monkey had to wait until the central target disappeared, which is the go signal, and only then to reach the cued peripheral target. If the monkey moved to the cursor to the correct target within the predefined time limits, it was rewarded with a drop of applesauce. We termed each recording date as a session. Each session was composed of 3 subsessions of trials, each of which had a fixed order of trials. Each subsession began with 64 trials to all 8 targets and 30 control trials to a single target. This was followed by a sequence of force field trials or HFS trials alone, and also trials that combine both force field and HFS, which were separated by washout trials. Adaptation was quantified using the hand deviation from the straight line, which were measured twice for each trial, at 150 milliseconds as indicated by the green marker, and at the end point of maximal deviation as indicated by the purple marker, forming 2 separate adaptation curves. Studying the effect of HFS on motor behavior, we were able to replicate our previous findings. As shown in this example, HFS increased movement variability even when no force field was applied. This effect, however, was more pronounced with force field. Dividing the adaptation sequence into bins of 5 trials emphasizes impaired capacity to converge to the straight line with HFS compared to normal adaptation. Next, we quantify the effect of HFS has on adaptation. Here, movement deviations were also measured at 150 milliseconds and at the maximal deviation. When measured at 150 milliseconds, HFS significantly affected the slow phase of adaptation from the 5th trial and on, illustrating significantly higher residual errors compared to normal adaptation. At maximal deviation, adaptation under HFS was affected both during the fast and slow phases of adaptation. We also quantify the effect of HFS on adaptation by analyzing the motor performance during catch trials. For this purpose, catch trials were integrated within adaptation sequence, both with and without HFS, as you can see here. This example illustrates the pattern in which movement deviations during catch trials consistently get more negative as deviations during force field trials become smaller. To quantify the effect of HFS on catch trial performances, we use the learning index that was previously suggested by Chen and colleagues in 2006. The learning index expresses the ratio between the deviation during catch trials and the neighboring force field trials. Corresponding with our previous results, application of HFS during adaptation significantly decreases learning index values here and here. However, analyzing only the differences between the mean adaptation curves may overlook other properties of a single adaptation sequence, such as the amount of noise within it, here and here. An adaptation curve such as this one here is characterized by a reduction in movement deviation as the trial number increases. In other words, we expect to get negative correlations between the deviation and trial number. In the mean adaptation curve, the amount of noise is low, and accordingly, the correlation coefficient is minus 0.85. For a single session during normal adaptation, there is additional noise, so the correlation coefficient is only minus 0.6. With HFS, the coefficient gets even weaker to a level of minus 0.2. This analysis was applied to all sessions, once when analyzing only the first 10 tries of an adaptation sequence, and again for all tries within an adaptation sequence. In both cases, we found significant reduction in the negative correlation values during adaptation with HFS. This suggests that HFS interferes with the consistency in which movement errors decrease during adaptation, both during the fast and the slow phases of adaptation. The state space model of learning describes adaptation as a process involving interaction between learning and forgetting. Learning is controlled by error sensitivity, and forgetting is controlled by the rate of memory decay that is referred to retention factor. Here we use the state space model to find the parameters A and B that best fit to the data, and found that during HFS, error sensitivity decreases, and to a lesser extent, the retention factor. Next, we model the data using the equation suggested by Albert and colleagues. We found that HFS significantly decreases error sensitivity and may also affect the retention factor. Just as smaller errors can be used more reliably to correct error of the next movement, the error sensitivity may become higher with smaller errors. To confirm this notion, we plotted the error sensitivity as a function of the error size. Although significant differences were illustrated between force field trials with and without HFS, both modes illustrated the same trend as I just described. We further aim to understand the mechanism under which HFS operates. As shown in this example, HFS trials look noisier than control trials. To quantify the noise within a sequence of trials, we first collected the maximal deviation values of all trials within a sequence and calculated the variance of these values. We did that for all sessions and paired the control variance with the corresponding variance of the HFS trials of the same session and got this scatter plot. The red dot in the scatter plot refers to the variance of the control and HFS trials seen in this example on the left. This scatter plot indicates that HFS significantly increases the motor noise compared to control trials. However, we have yet to uncover how this noise is related to the error sensitivity properties. We also didn't yet rule out the possibility that HFS functions as an additional source of external noise. To answer this, from all sessions, we chose only those with similar amount of noise
Sharon, you have 5 minutes.
And recomputed error sensitivity. We found that HFS significantly decreases the error sensitivity, even when the noise level between control and HFS trials are matched. These results might suggest that the motor noise we measured is independent of the error sensitivity. Finally, we aim to exclude the possibility that HFS disturbs adaptation by adding external noise. If HFS functions as an external noise, it would be expected to have similar effect as perturbation does, even when no force field is turned off, even when the force field is turned off. Tanvi and Smith in 2018 added external noise to a visual motor rotation task in the form of perturbation variability and measured the adaptive response to this noise as defined here. They found a clear adaptive response to externally applied noise, while no response to internal noise of the same magnitude. Here we first measured the adaptive response during controlled tries and compared it to adaptive response during force field tries and found significant differences between the regression lines. However, we found no difference between the regression lines of controlled tries compared to HFS tries. These findings illustrate that HFS doesn't trigger adaptive response as external perturbation does. Namely, the added noise during HFS may be considered as an internal noise. To summarize our behavioral findings, HFS affects adaptation by three means. One, HFS inhibits adaptation and presents increased residual errors. Two, HFS decreases learning index that was computed by using the catch tries. And three, HFS disrupts the consistency of reduction in movement deviations during adaptation. We were also able to model the data and found that HFS decreases error sensitivity, at least partially independent of the level of internal noise. Also, we were able to exclude the possibility that HFS disturbs adaptation by merely adding external noise. Currently, we are analyzing the effect of HFS on single cell activity and looking for cells neural correlates of motor behavior. This raster plot and PSTH were recorded during a complete subsession in trials were directed to a single target. This cell's preferred direction is directed toward the learned target. The red boxes show the sequences of trials with HFS, and the blue boxes show the force field trials. As you can see in these regions where HFS was applied, there is a clear reduction in firing rate around the movement onset, even when the force field was not activated. The decreased neural activity with HFS that is illustrated in the PSTH emphasizes the robust effect of HFS on cell activity beyond the effect that the force field has on it. Likewise, we found that the mean PSTH during adaptation with HFS decreases compared to control tries. To statistically establish this observation, for each cell, we subtracted the baseline activity from the mean PSTH peak activity around movement onset to get the response transient activity. We paired this activity transient between corresponding control and HFS tri sequences and found significant reduction in cell activity with HFS. Next, we aim to study the effect of HFS on the modulation of cell activity over the course of adaptation. As a preliminary study, we did the following. We first identified cells that change their firing rate along adaptation trials, and then divided these cells into two groups: cells that decreases their firing rate during adaptation and cells that increase their firing rate during adaptation. For each cell, we correlated its spike count per trial during the adaptation sequence with the error in the corresponding trial. In cells that decrease their firing rate during adaptation, we expected to find positive correlation, as both the spike count and movement deviation decrease. In cells that increase their firing rate, we expect to get negative correlation since the spike count and movement deviations have opposing trend. We applied this procedure for all cells, both during adaptation with and without HFS. For the two groups of cells, we plotted two histograms of firing to error correlation values. We found that in both cell types, HFS significantly decreases the correlation between spike counts and the error. To summarize the final two slides, on the effect of HFS on single cell activity, we can say that HFS decreases single cell activity in control conditions and also during force field trials. About 50% of the recorded cells illustrated modulation of firing rate during adaptation. These cells had strong correlation to the magnitude of error. In the near future, we intend to study whether cells firing pattern also express the differences in error sensitivity between normal adaptation and adaptation with HFS. I want to thank all the people that helped and are still helping me in carrying out this project. Professor Ifat Prut, Professor Firas Mawasef from the Technion, Dr. Ran Aral from Sheba Medical Center, and my friends and colleagues Abed and Nirvik, and to all the other people from our lab. Thank you very much.
Well, thank you, Sharon, for a really cool talk. I'll get the questions started. So you showed that this high frequency stimulation increased variability. So I guess my question is, would you also expect that this would improve? So they were reaching one target, correct?
In each session to only one single target.
So would you expect that the condition, the HFS condition, would lead to improved generalization to other targets?
Excuse me, can you repeat the question?
Would you expect that the HFS condition, given the increased uncertainty, would lead to increased variability, would lead to increased generalization to other movement directions?
I think, okay, we actually didn't examine how HFS affect generalization to other movement directions. What I'm expecting, maybe it might affect generalization. We don't know. Like maybe we can test it maybe in our other studies, but we didn't check it yet.
No, I realize that. I guess I'm just was probing your prediction.
Like I mean, okay, if it's cerebellar property generalization, so I guess it might affect the generalization to other movement directions. That's my thought, but we didn't check it yet. So
okay. And we have a question from Reza Shadmir. He says, beautiful work. Would you tell us where the cells recorded from?
They recorded from M1 and premotor cortex, and also from somatosensory areas.
Okay.
And in this stage, we didn't differentiate between the different areas. Like we took all the cells that were recorded. We are planning to also differentiate between areas and to check if there are differences between motor and premotor areas, and to see if it might change the preparatory activity, like if the preparatory activity is different between M1 and premotor cortex. But not yet.
Okay, all right. Thank you. Thank you for that great talk. Okay. All right, so now we're going to move on to the last talk of this session before our plenary speaker. So Ihsan is going to, from Reza Shadmir's lab, is going to be telling us about synchronous spiking of cerebellar Purkinje cells during the control of movements.
Oh, I should first unmute myself. Cool. And thank you very much, Aliyah. Can you hear me? Everything okay? Can you see my screen?
Yeah, looks good.
Yeah, cool. Perfect. Thank you. Thank you very much for the organizers for doing this MLMC again this year as well. My name is Ehsan Saragat Nejad. I'm a PhD student at Shatner Lab at Johns Hopkins University. The title of my talk today is Synchronous Spiking of Cerebral Purkinje Cells During Control of Movements. And this was a collaborative project with Paul Hage, JP, and Amin Fakharian, all PhD students at Shatner Lab. And before I start, for those of you who participate in SFN 2021, Reza will give a 1 hour long and one of the special lectures on Monday titled Learning from Prediction Error. I highly recommend this, like you should not miss this one. And on Thursday from our lab, we will have 3 posters. I will discuss synchronous spiking in Purkinje cells, and the same project that I'm going to present for you today. Paul will discuss his new findings for saccade-related neurons in vestigial nucleus, and Jay will present this very cool project. You will see some hint of it in my talk today as well, encoding of sensory but not motor events via complex spikes of Purkinje cells. It's really good that I'm following Sharon, but it's no surprise to you that patients with cerebral degeneration have difficulty controlling their movements. Here is a patient with degeneration along vermal regions of the cerebellum, and you can see these jittery movements at the end of the movement, the saccades. So these patients usually can initiate their eye movements, and sometimes the reaction time is lower, but most of the times even the reaction time is okay for initiating the movement, but they have very difficulty controlling the endpoint accuracy of the movement. For example, here you can see that for a normal healthy subject, and the subject made the eye movement, made a corrective saccade and landed on the target, but this patient couldn't land on the target, and the saccade was hypermetric. And then when the patient tried to make a corrective saccade, even the corrective saccade was again hypermetric. So the question is, how does the cerebral cortex contribute to control of movement deceleration? And I'm highlighting deceleration because this is about stopping the movement. Okay, so previous other labs also have worked on this question. And this beautiful work by Abigail Person and Indira Raman, and really inspired me and the lab for this work. Is that, and there are 2 ideas in this work. First of all is that Purkinje cells are not alone, and they are bundles of Purkinje cells. And Abigail showed that there is a 50-to-1 mapping from Purkinje cells to the downstream DCN neurons, and they together project and drive downstream DCN neurons. And the second cool idea is that although the Purkinje cell input to the DCN neuron is inhibitory, but when Purkinje cells get synchronized with each other, then instead of inhibiting the DCN neuron, they actually entrain and invoke a spike in the DCN neurons. David Hirschfeld, who was a PhD student in our lab at the time, reanalyzed the macaque data from our colleagues in University of Washington, and he showed that when we use encoding of the error and complex spike activity, we can tackle the first idea here to bundle the Purkinje cells together, because here this is in vitro studies, but in behaving animals, it's in vivo, and we don't usually easily have access to the cells, but using this idea, we can bundle the cells together. However, what this study didn't address is the synchrony question. So the question is, does the cerebral cortex rely on a spike synchrony within populations of Purkinje cells to control movements? So in our lab, we built a marmoset lab. We trained marmosets to perform saccadic eye movement task. And while the monkeys, marmosets, were performing this eye movement task, we recorded from oculomotor vermis. So these are Purkinje cells that have encoding for the eye movements. Here's a sample recording from a Purkinje cell. And we also developed a software named PSORT, and using PSORT, we sorted the simple spikes and complex spike of these Purkinje cells. Okay, I will first describe the complex spike activity of these Purkinje cells, and I will then shift my focus to the simple spike activity. So the tasks started with the monkey fixating at the center of the screen, and after 200 milliseconds, we jumped the target to a primary location randomly in one of 8 directions. And then because of this target jump, and the animal make a primary saccade, the blue traces here. And now if you look at the complex spike activity aligned to the target jump, whenever we introduce this unexpected visual event, we saw that Purkinje cells have a preferred direction. In their preferred direction, the complex spike activity will rise. And in the opposite direction or anti-preferred direction, the complex spike activity will go below baseline. Continuing the task, and when we detect the onset of the saccade, we jump the target again randomly, and then as a result of this, monkey will make a secondary saccade. Now, when we look at the complex spike activity during the offset of primary saccade, this is the time when the animal actually experienced the secondary target jump. We again see a similar pattern. The monkey will continue fixating on the secondary target for 200 milliseconds and then receive its reward. The task continues. Monkey will again keep fixating at the preferred target. Then after a random period of time, we'll jump the target back to the center of the screen. And so the monkey has to make a third saccade, what we call a back to center saccade, and to go back to the center of the screen and start the next trial. And if you look at this target jump, because the timing of this target jump is random, we interestingly saw a similar pattern to the primary saccade and secondary saccade. So we put all these three types of saccade together and we call them targeted saccades because all of them are in reaction to a target jump. And what we saw is that in the preferred direction of the Purkinje cells, we saw an increase in the complex spike activity of the cell, and in the anti-preferred direction, we saw a reduction in the complex spike activity. Okay, this was toward the target jump. So there is some debate in the literature about does complex spike react to the target jump visual stimulus and visual events or motor events. So what I plotted for you was with respect to target onset. Now I'm going to reanalyze the data, but now align everything to the saccade onset. So when we look at the activity of these cells aligned to the saccade onset, indeed, we saw that before saccade onset, we had an increase in the preferred direction and decrease in the anti-preferred direction. But keep in mind that this period of time after target onset onward or before saccade onset backward is actually shared between these two events. So how can we disentangle these two things is that now we look at what we call other saccades. So from time to time, the animal will actually break the fellow of the experiment and do some make some saccades in the void. And these saccades are usually when the animal is harvesting the target. But the most important part is that at the onset and the offset of these saccades, there is no target on the screen. So when we look at the activity of complex spike during these task irrelevant saccades, what we saw is that there is a slight modulation in complex spike activity, but this is no way near the modulation that we saw with the targeted saccade. So as a take-home message, complex spike encodes sensory events and not motor events. And to see more cool analysis and also some control experiments for these take-home message, please visit Jay's poster on Thursday. Okay, so I showed you that Purkinje cells have a preferred direction, what we call CS on, and an anti-preferred direction, CS off, that the activity will go below baseline. If we plot the probability of getting a complex spike in different direction, indeed, we saw preferred direction, we get higher probability of getting a complex spike, and anti-preferred direction, lower probability of the complex spike. But in other direction, we saw this tuning curve for the Purkinje cells. We recorded from different Purkinje cells at different point in time. And indeed, what we saw is that different Purkinje cells have different preferred directions. So not all of them have similar preferred directions. But I'm going to first tell you what we did, and then I'm going to tell you why we did that. So what we did is that for each Purkinje cell individually, we are going to rotate the coordinate system. So I'm rotating the coordinate system now. I'm going from a Cartesian coordinate system to a CS-based coordinate system. And we made it as if all these Purkinje cells have a preferred direction for 0 degree. So all of them now, all of these Purkinje cells recorded separately have similar preferred direction. So why we did that? This is because we hypothesized that when Purkinje cells receive the same inferior olive input, and they will have the same preferred direction or same encoding for the error. And more importantly, this bundle of Purkinje cell will together project to a downstream DCN neuron. So when we organize our data in this way, then we can put them together as a population and look at the some activity for the population. So we organize P cells into a population that shared a similar preference for error. Okay, before I show you the simple spike activity, let me show you for the population some simple spike activity for individual P cells. So in our data set, we saw a diversity of Purkinje cells. We saw P cells that burst in their activity during the second, burst, pause, burst, or completely pause during the activity. And what is common among many Purkinje cells in our data set is that most of them, the activity lasts much longer than the second itself. So I started with encoding of the movement and basically controlling the endpoint accuracy, but these Purkinje cells, the activity lasts much longer than the second. So how can they contribute to the endpoint accuracy? Well, again, when we transform our coordinate system using complex spike, and now we are going to look at the simple spike activity. What we saw for the simple spike activity in the population of 149 T cells, what we saw is that as a population, simple spikes will burst in their activity before the second onset and will pause during the second itself. And then the duration of the pause precisely predict the endpoint location of the second. So individually, they don't predict the endpoint location of the second, but as a population, and the population activity precisely predict the endpoint location of the second. This effect was prominent in direction CS180. We saw a similar effect in other direction, but it was not as prominent as what we saw in direction CS180. So this is the average activity for an average second. What about different kinematics for different seconds? So here I'm aligning the data to the peak velocity or deceleration onset. And if you look at the activity of, again, population of P cells, we saw that as a population, for different peak velocities, if you look at the peak burst before the second, there's a linear relationship between peak burst and then peak velocity. And the other thing that I should highlight here is that the peak pause also is time locked to the deceleration onset. Although there is a linear encoding of peak velocity by peak burst, there's not that much encoding of the peak pause, and the encoding and the peak pause is not getting modulated by peak velocity. Again, this effect is most prominent in direction CS180. It is present in other direction, but it is not as prominent as what we saw in direction CS180. Okay, so simple spike and burst predicted the kinematics of ensuing eye movement, and simple spike pause was time locked to onset of the second deceleration. Okay, so I started my talk with the question of synchronous activity among population of P cells, and how can we do we see the synchrony in population or not? In our data set, within that 149 individual P cells, we have 42 pairs of simultaneously recorded P cells. So here's an example pair. What you can see is that for a pair, simple spike activity does not usually go along with each other. For example, this pair, one cell is bursting after the second, so pause burst, but the other cell is completely pausing during the second. What we saw in our data set is that the pairs usually show a similar CS-on tuned.
Hassan, you have about 4 minutes.
Sure. Okay. Now, if you look at synchronous activity, so how did we define synchrony? So we had the first P cell, and here's a raster plot for the cell. We had the second P cell, and using these two, because we simultaneously recorded them together, we can compute the joint probability between these two cells. And then we can also compute the chance or independent probability of getting a spike from either of these cells. We define our synchrony index by joint probability normalized by independent probability or chance level. Okay, so now let's look at the synchrony among population of Purkinje cells, synchrony between simple spikes. What we saw is that, this is actually surprising, that during the burst period before the second onset, the synchrony stays at the baseline level. It is during the pause or during the second itself that the synchrony will start increasing, and then reaching its peak synchrony after the peak velocity or deceleration onset and before the saccade offset. Again, we saw that this effect, this synchrony effect, is present in other direction, but is most prominent in direction CS180. Okay, so this is my last slide. I started with this question of how does the cerebral cortex contribute to control of movement deceleration? We recorded from 149 P cells, and we organized P cells into populations that had a similar preference for error. And when we did that, what we saw is that as a population, simple spike activity, the maximum burst predicted the kinematics of the eye movement. The maximum pause was time locked to the onset of the saccade deceleration. And regarding synchrony, there was a temporal alignment of spikes and that coincided with the movement deceleration. So to address this question of how does the Purkinje cells contribute to the movement deceleration, we think that the Purkinje cell will inhibit with baseline synchrony and inhibit the DCN neurons to disinhibit them during the saccade or during the onset of the deceleration. And since they are disinhibiting, there is less number of spikes. But what the P cells are doing is that they are getting more synchronized because synchrony will actually invoke more spikes and to actually increase the probability of invoking the DCN neurons. So the Purkinje cells are just setting the DCN neurons to fire during the deceleration phase of the movement and to control the endpoint accuracy of the eye movements. And for more results and more details, please check my bioRxiv paper that is available for you. So with that, I would like to take your questions. Thank you very much.
Oh, thank you, Ehsan. That was a great talk. Really beautiful slides. So we have a number of questions. So from Ian Greenhouse, very interesting data. How many synapses are there between the P cells and the eye muscles controlling saccades?
Sure, yeah. So I don't have the plot here, but P cells will go to DCN. Then from DCN, there's a projection to the burst generators in the brainstem. So IBNs and EBNs, inhibitory burst generators and excitatory burst generators. From burst generators to the motor neurons, and from motor neurons to the eye muscles. So DCN, burst generators, and then motor neurons. So 3 synapses. Or 4, yeah, 3 synapses to the eye muscles, yeah.
And we have another question from Amir Abbasi. They ask, did you look at complex spike activity aligned with reward?
Yeah, very great question. We did not, but this is a really cool question, and we have the data to look at that. Because we also record the tongue movement, so we can actually mark that, and we have plans to do that. But I don't have a clear answer for how does complex spike encoding reward. And of course, Matthew Joshua has worked on this, and you can check his work. He had a really cool work in this regard.
All right, well, I think in the interest of time, we should move on so we can stay on schedule to our plenary speaker. So thank you so much for the talk. I will introduce our final speaker for the meeting, Friedel de Groot. Friedel, do you want to share your screen?
Trying to do so. Wait. Oh yeah, I see. Okay, I'm going to share.
Okay. So it's really my pleasure to introduce our final speaker of the day. Friedel de Groot is at KU Leuven, and she's a pioneer in developing musculoskeletal models of movement and has made really impressive cutting-edge contributions to the development of predictive simulations of movement using optimal control. And these simulations have provided a real deeper understanding of the neuromechanics of movement in both healthy and clinical populations. And I saw recently, I was looking over your publications, and I saw that now you're applying these tools to dinosaur locomotion as well. So I'm excited to hear your talk.
Okay, thank you for the introduction, and thank you for inviting me to speak here. I have to disappoint you because I won't be talking about dinosaurs. But in this talk, I will address stochastic optimal control. So as a bit of a general introduction, so I think model-based simulations can give us unique insights in neuromechanics of human movement, because in simulation, we can alter isolated properties of the neuromusculoskeletal system and evaluate their effect on the movement pattern. And for example, we can evaluate how reducing muscle strength alters the gait pattern, as you can see in this movie where we reduced hip muscle strength. And therefore, simulations can complement experiments where it is often unfeasible to study the effect of isolated properties of the neuromusculoskeletal system. Simulations are based on a model. Musculoskeletal dynamics describe how muscles transform excitations into muscle forces, how these forces are applied to the skeleton, and how the skeleton moves under the influence of muscle and external forces. In addition, we need to model motor control. And very often it is assumed that motor control is optimal in some sense, for example, by minimizing muscle effort. And we can then find the optimal neural controls or control policy by solving an optimal control problem. Optimal control simulations have been used to study both biomechanics and motor control. Yet the simulation approaches used in these two domains are very different. In biomechanics, the focus has been on loads and movement patterns. The musculoskeletal system, which is a main focus of biomechanical analysis, is represented in detail. So nonlinear differential equations describe muscle and skeleton dynamics. Sensory motor noise and uncertainty about the environment are ignored. And as a consequence, the resulting optimal control problems are deterministic and typically solve for open loop muscle controls that drive the movement. Such simulations do not yield control policies and are therefore unsuited to answer questions related to feedback control. In contrast, in motor control simulations, these are used to answer questions related to feedback control and movement accuracy and variability. Musculoskeletal dynamics are typically simplified. Often few degrees of freedom are considered and dynamic equations are linearized. Sometimes the musculoskeletal system is even represented by a point mass. But physiological noise is accounted for, resulting in stochastic optimal control problems that yield control policies. And in general, these control policies are a combination of feed-forward and feedback signals. Because of these different approaches, most simulations do not account for the interaction between nonlinear mechanics and control in the presence of noise. Yet, mechanics and motor control interact, and I therefore believe that we need to combine complex mechanics with control policies that are robust to noise to advance our insights in both biomechanics and motor control of movement. But doing so results in optimal control problems that are hard to solve. We were recently able to reduce the computational cost of deterministic simulations of walking based on complex musculoskeletal models by a factor 20. In these simulations, we minimized a cost while imposing muscle and skeleton dynamics, as well as a desired walking speed and symmetry of the movement. The resulting deterministic optimal control simulation resulted in a physiologically plausible walking pattern, as you can see in this video. In addition, our simulations of walking capture the effect of muscle weakness and prosthesis use. Here you see that our simulations in red capture experimental alterations in ankle joint torques in gray due to prosthesis use. Yet our simulations do not capture how people stabilize their movements against noise, which I feel is an extremely important feature of human movement that is often impaired in neurological disorders. To account for the effect of noise, we are developing a stochastic optimal control framework to simulate nonlinear mechanics in the presence of noise. So in general, we consider the musculoskeletal system that interacts with a noisy environment. The state of the system is sensed by noisy sensors, and compared against a desired movement trajectory. Deviations between the sensed and desired movement trajectory result in feedback corrections that are added to feed-forward commands. And these neural commands drive the muscles, and the transformation between neural commands and muscle force is again noisy. The control policy is determined by the feed-forward excitations, the feedback gains, and the desired trajectory. We solve for these control parameters by minimizing expected effort, subject to the system dynamics and task constraints, while imposing that the movement should be stable. We can solve these problems efficiently by leveraging computational tools that have been successful to solve deterministic optimal control problems. And to this aim, we approximate stochastic optimal control problems by deterministic optimal control problems. In the presence of noise, the state, which typically includes the positions and velocities, is variable. And we approximate the state distribution by a Gaussian distribution. And as a result, we can represent the state distribution by the mean state and the state covariance. And in a general case, the dynamics of the mean state is nonlinear. We also need to describe the dynamics of the state covariance. And so far, we have used two approaches to do so, either a local linearization of the state covariance around the mean state, or an incentive transform to approximate the state covariance. And we then solve the resulting deterministic optimal control problems using direct collocation. And with this approach, we have been able to simulate nonlinear mechanics in the presence of noise efficiently, although we are not yet at the same model complexity as with our deterministic simulations. So in the remainder of this presentation, I will share some insights we gained from applying our stochastic optimal control framework to reaching, standing balance, and walking. So optimal control simulations of reaching are often based on point mass models. And such simulations capture some, but not all features of reaching mechanics. And here we investigated how nonlinear mechanics shapes reach trajectories. To this aim, we reproduced the experiments described by Neshet et al. In simulation. And so subjects reached to a circular target, to a bar, and to a circular target through an obstacle. And some of those reach movements were perturbed, eliciting or showing the feedback control. Neshet et al. Also performed optimal control simulations based on a point mass model. So instead, we modeled the musculoskeletal system as a two-segment aura model driven by two pairs of antagonistic muscles. And these muscles were activated by a combination of feed-forward and feedback activations, where feedback was described as linear feedback of the end effector or hand kinematics, which was compared to a reference or nominal end effector trajectory. Feedback muscle excitations were then generated based on a linear time-varying feedback law. And reaching to the different targets was simulated by imposing the end effector accuracy in the horizontal and vertical directions in different ways. So also here, the control policy was described by feed-forward muscle excitations, time-varying feedback gains, and a reference end effector trajectory. And we estimated control parameters by minimizing expected muscle effort. And we tested whether simulations based on this musculoskeletal model were more accurate than predictions based on a point mass model, which would indicate the importance of taking the nonlinear dynamics into account. Here you see unperturbed endpoint trajectories. So in black, you see the experimental data from Neshet et al. In gray, the results from their simulations based on a point mass model, and in color are simulations based on the more complex musculoskeletal model. Kinematic trajectories simulated with both models are similar. and note that the horizontal deviations are not corrected when reaching to the bar in agreement with the minimal intervention principle. But Nashet et al. Also analyzed the response to perturbations, and we thus also performed simulations of perturbed reaching by performing forward simulations under the optimal control policy. Simulations of perturbed reaching trajectories based on the musculoskeletal model in color are in better agreement with the experimental data in black than those based on the point mass model in gray. So in agreement with the experimental data, the musculoskeletal model predicts later corrections than the point mass model. And the musculoskeletal model also predicts an overshoot, which in the bar condition is strikingly similar to the experimental data. So to summarize the results, under the same optimal control assumption, the more detailed model preserves control features predicted by simple models, such as the minimal intervention principle, and improves the prediction of perturbed reaching trajectories. But because we use or remodeled muscles, we can also evaluate corrective muscle activity. And here this corrective muscle activity is shown for the 4 muscles in our model. Experimental data was only available for the anterior deltoid and biceps in the circle and bar conditions. But you see that our model prediction that corrections are larger in the circle condition in blue here than in the bar condition in red here are in agreement with experimental data. So inclusion of muscle dynamics allowed us to validate the motor control hypothesis, in this case, minimal effort at the muscle level. So summarized, simulating nonlinear mechanics improved the realism of the simulated kinematics and will allow us to validate motor control hypothesis at the muscle level. Next, we used our stochastic optimal control framework to evaluate whether optimal control predicted muscle co-contraction during perturbed standing. Co-contraction of antagonistic muscles is frequently observed during movements that are new or challenging. For example, co-contraction is higher when walking on uneven than on even surfaces and during perturbed standing in older adults than in younger adults. Co-contraction might stabilize movement by increasing the mechanical impedance of the joint. Muscle stiffness and damping is activation dependent through the muscle's force length and force velocity properties. And in addition, short range stiffness provides a strong resistance to initial stretch that scales with baseline activity. So we explored this mechanism by performing simulations of perturbed standing balance based on an inverted pendulum model that was driven by a pair of antagonistic muscles. The model was perturbed by translations of the platform, and we considered 2 types of muscles, either hill-type muscles that describe the force length velocity relationship of muscle, or a hill-type muscle extended with short-range stiffness. The activation of these muscles was a combination of a constant feed-forward activation and feedback. And feedback activations were a linear combination of proprioceptive and vestibular feedback that was corrupted by sensory noise. The feedback gains were constant for a given perturbation level. And we solved for feed-forward muscle excitations and feedback gains that minimized expected effort. And in this case, we imposed the desired reference, that is upright standing. We evaluated simulated body sway for different magnitudes of quasi-random platform translations. Body sway increased with perturbation magnitude and was similar for both muscle models. We also evaluated co-contraction and found that there was no co-contraction for the hill-type muscle, but that co-contraction increased with body sway when short-range stiffness was modeled. Hence, we predict co-contraction as a minimal effort strategy. However, the activation-dependent stiffness of the muscle and the perturbations have to be sufficiently high for the effort related to co-contraction to outweigh the expected effort of the feedback corrections. However, there is also a second mechanism through which co-contraction might improve stability, and that is dual agonist-antagonistic control. Co-contraction of an agonist-antagonist pair of muscles may improve control by allowing both the excitation of the agonist and the inhibition of the antagonist in response to perturbation. Yet the simulations I just showed do not capture this mechanism because we used a local linearization to propagate the covariance matrix. So although we constrained activations to be between 0 and 1, the optimal control problem fails to see that it cannot make corrections by reducing the activation under 0. And to solve this problem, we performed simulations using a different approximation to propagate the covariance. So in this case, we decided to not model muscle mechanics and instead to use two antagonistic torque actuators. And as such, we could attribute co-contraction to this agonist-antagonist dual control only. And so again, we considered feed-forward and feedback activation, and we used both a local linearization and an uncentered transform to propagate the covariance matrix. In agreement with the simulations based on the Hill type model, we did not find co-contraction when using this local linearization of the covariance matrix, as you can see in blue here, as again, the model failed to see that it needs baseline activity to be able to reduce muscle activity, but we found co-contraction when using a more accurate approximation to propagate the covariance matrix. Hence, also dual agonist-antagonist control is a minimal effort strategy for higher perturbation levels. So in conclusion, co-contraction may be a minimal effort strategy to stabilize movement. And this brings me to walking. And here our central question was, does optimal control capture experimentally observed sensory motor transformations during perturbed walking? We have recently investigated sensory motor transformations underlying control of perturbed walking balance in multiple data sets. So inspired by research in perturbed standing balance, we explored the relation between corrective ankle torques and delayed center of mass kinematics across data sets. So experimental protocols included discrete pelvis pushes, discrete support surface translations at multiple instants within the gait cycle, and continuous support surface translations. Here you see example center of mass position, velocity, and torque and ankle torque trajectories for nominal walking in gray and when applying pelvis pushes or pulls in color. And we explored correlations between the corrective ankle moment and the deviation in center of mass position and velocities 100 milliseconds earlier. Across data sets, we found that the corrective ankle torque correlated with the center of mass position and velocity 100 milliseconds earlier, and that the corrective ankle torques could be well reconstructed by delayed feedback from center of mass position and velocity. The continuous perturbations allowed us to investigate how center of mass feedback gains were modulated throughout the stance phase and with gait speed. So here you see the position and velocity feedback gains as a function of the stance phase. So these are Kp and Kv. And darker colors correspond to lower gait speeds. So feedback gains were negative, but their absolute value is largest in mid-stance and when walking slower. And we then used our stochastic optimal control framework to evaluate whether optimal control could reproduce these experimental observations. We used a relatively simple 5-segment torque-driven model with impulsive collisions. So at each time instant, only one foot was in contact with the ground. We assumed that the fill state, consisting of joint angles and velocities, was sensed and compared to a desired state. The feedback error was corrupted by Gaussian sensory noise and multiplied by time varying gains to obtain the feedback torques. And feedback torques were added to feed forward torques, and the total torque was corrupted by Gaussian noise. And again, we solved for the control policy by minimizing the expected sum of torques squared, while imposing the desired speed, periodicity, and stable limit cycle behavior.
Italy, you have about 5 minutes.
Okay, perfect. The obtained optimal control policy yields simulations of walking that are robust against noise, in contrast to the deterministic open loop controls that I showed just on top, like the top ones. So we used our optimal control policy to perform simulations of walking in the presence of support surface translations, mimicking the experiments of Moore et al. That we previously analyzed. And we evaluated the relation between center of mass kinematics and corrective ankle torques, as we did for the experimental data. So here you see the experimental data again on the left, and on the right you see the results we obtained based on our simulations. In agreement with, so we found a qualitative agreement between the experimental data and the gains determined from experiments and the gains determined from our simulations. So also in simulation, the absolute value of the feedback gains was larger for slower than for faster walking speeds. And in simulation, and that's where you see on the bottom, the ankle torque could even be explained better by center of mass feedback than in the experiments. And note that we did not model center of mass feedback. We just modeled linear fill state feedback. And so this center of mass feedback is like an emergent property. And we are not so surprised about the quantitative differences because we use this very, very simple model of walking. So in conclusion, we believe that our stochastic optimal control framework can bridge the gap between biomechanics and motor control simulations. By combining nonlinear mechanics and noisy control, we were able to test motor control as a theory of movement coordination beyond what has been done previously. We found that having more detailed models of musculoskeletal mechanics improves predictions of kinematics under the same optimal control assumptions. We found that muscle co-activation is a minimal effort strategy in the presence of activation-dependent muscle stiffness or nonlinear activation. And we demonstrated that stochastic optimal control captures sensory motor transformations underlying walking. And with this, I want to acknowledge Tom van Wouwen, who developed the stochastic optimal control framework and performed the simulations, Maarten Afschrift, who explored the sensory motor transformations during walking, and Lina Ting, with whom we collaborated to develop the stochastic optimal control simulations.
Right, thank you so much, Friedel, for that really exciting talk. I love how this work bridges the biomechanics and motor control worlds, and is so helpful. So we have a number of questions. So from Reza Shadmir, this was earlier in the talk, very impressive work. In your simulations of Nishid et al., did you also include a model of the robot dynamics?
No, we did not. So no, we did not. That's a very short answer.
Yeah, I'm trying to remember which robot, likely the kin arm. Okay, so let's move on to the next question from Adrian. Muscle effort, as in U squared, is quite an abstract and arbitrary cost in contrast to the very, very detailed musculoskeletal models. So how might your results differ if you considered an alternative cost more closely related to metabolic cost? So I guess, are you using U squared or are you using Brian Umberger's model of metabolic cost?
Yeah, so for the stochastic optimal control simulations, we are using U squared. But for simulations of walking, we use like the deterministic simulations of walking. We used a multi-objective cost function. And there we really explored the effect of the cost function on the walking pattern. And I think those deterministic simulations of walking really tell you something about steady state walking in really stable environments. And so there we found that we needed a combination of metabolic energy rate squared, muscle activity squared, and joint acceleration squared to obtain like physiologically plausible gait patterns. And so my thought is like only metabolic cost didn't work because then we got like a very uneven distribution of the activity over different muscles, with some muscles being maximally active, which I don't think happens during walking. And that might be because our metabolic energy models are still off, like as well as our muscle mechanics models. But it might also be because we don't only care about efficiency or like metabolic efficiency, but also about fatigue. And then I'm not so happy with having to minimize joint acceleration squared in like the deterministic simulations. And I have been wondering whether that might be due to not accounting for noise, because I think that in reaching it has been shown that you can get those bell-shaped velocity properties both by minimizing jerk, which is then the derivative of acceleration, or by accounting for noise. So yeah, I definitely think our cost functions are still very, very simple, and I also think we have to further increase the detail in our mechanics. This will require us to improve the efficiency a little bit more. Right now, stochastic optimal control simulations take a minute or 2 minutes for the examples I showed you, but like they don't scale really well with the number of states, because we have this covariance matrix that grows quickly. And so we are now exploring different approaches, to make this work for really complex mechanics.
All right, and so we have a related question. You may have just touched on this, but I'll ask it anyway. Have you examined signal-dependent noise, and could signal-dependent noise influence the trade-off of muscular co-contraction and feedback gains from an energetics perspective?
The short answer is no. We haven't made a very detailed comparison of like signal dependent noise versus just motor noise, and I think it's a really interesting question, and we should definitely look into that. But I find it hard to make predictions there, and I also would say. So what we have done is we have looked at, so for the perturbed standing balance, we have simulated vestibular Ross subjects, and I think that kind of changes the noise structure, and that had an influence on co-contraction. So I really think the amount of co-contraction we will find will depend on this ratio between sensory and motor noise. So if the signal dependent motor noise like increases the noise overall, I think it will lead to less co-contraction. So it's really, I think, this balance between how much sensory noise do you have because the more like, yeah. So yeah, it's sensitive to the noise levels. And I think that's the interesting thing, that we can now explore how it is sensitive to those noise levels. But on the other hand, it's also really hard to get experimental data on like sensory noise and like know where you are, and we can do those parameter sweeps. I mean, we've tried a little bit to estimate sensory noise levels, but it's tricky.
All right.
Wait, can I ask one question?
Yeah, go for it, Maurice.
So I saw, I mean, I see that if you found that co-contraction was optimal in terms of minimizing effort when you used a muscle model that had short range stiffness as opposed to the standard Hill model. But what I guess I didn't, I saw the finding, but I didn't understand. I guess I didn't really understand it. So what is it about having that sort of short range stiffness that makes co-contraction, reduce effort?
Mm-hmm. Yeah. So in a Hill type model, you have this. There is a force length velocity relationship of the muscle, and so it will give you some activation dependent stiffness and damping, but the stiffness of a Hill type muscle is pretty low. And so I think if the stiffness is low, you need high levels of activation to increase joint impedance, and high levels of activation are expensive. And in that case, it might just be better to use feedback if you want to minimize expected effort, because then you make feedback corrections, and those feedback corrections will be cheaper than the very high activations that you would need to get a considerable increase in joint impedance. But then short range stiffness, like your muscle is really, really stiff if it has been isometric and you stretch it. And so as long as your sway, and that's what Lina has shown, as long as your sway is limited, like this property of the muscles is preserved, even if you make small movements. And so if you are quasi-isometric, if your muscle fibers are quasi-isometric and you pull at them, you get a very high stiffness. And so if your stiffness is so high, we think that small levels of co-contraction can give you large gains in joint impedance, and this gain in joint impedance might reduce the feedback corrections that you need, and hence might reduce expected effort.
I see.
Does that clarify how we think?
Yeah, that helps a lot. Thank you.
I'm muted. All right, well, I thank you for that excellent talk, Friedel. It was great to hear about your work. And so all right, so okay, that brings us to the end of our program. We're just running a little over, but thank you all for those of you who are still here. And we hope that you enjoyed this meeting. It was unfortunate that was online, but who knows? Hopefully, maybe next year we can meet. I'll meet in person. So, all right. Well, thank you all, and we'll see you next year.
Yes, thank you, everybody.